What if, deep in the vastness of space, an alien civilization is trying to reach us? Or perhaps we've already received their message, but we just don't understand it yet. Over the decades, humanity has been scanning the skies with ever more powerful instruments, listening for signs that we're not alone. And while the universe seems endlessly silent every so often, something strange emerges from the deep. Mysterious signals that hint at the possibility that something is out there. Are these just random phenomena, or is something or someone out there trying to communicate? Let's explore the most compelling signals we've received, delve into the research that's been done to uncover their origins, and consider the implications of what it would mean if we were to make contact with an alien civilization. The beginnings of the search. SETI's role in exploring deep space signals. The origins of the search for extraterrestrial intelligence, or SETI, date back to the 1950s, a time when the world was adjusting to the rapid advances in technology that had come with the post-World War II era. The Cold War had sparked a race for scientific achievement, pushing nations to reach further into space, and it was in this climate that the possibility of detecting signals from other civilizations began to be seriously considered. Up until then, humanity's view of space had been limited mostly to scientific observations from telescopes and space probes. But with the rise of radio technology, new doors were opened. Radio waves, the same type of electromagnetic radiation used for communication on Earth, could travel across vast distances. Could they be the key to hearing from other worlds? One of the first to seriously propose the idea of using radio telescopes to listen for signals from intelligent extraterrestrial civilizations was Frank Drake, an astronomer at the University of California, Santa Cruz. In 1960, Drake conducted a pioneering experiment known as Project Ozma, named after the fictional Queen of Oz in L. Frank Baum's famous novel. With an 85-foot radio telescope, Drake scanned two nearby stars, Tau Ceti and Epsilon Eridani, which were thought to have conditions potentially suitable for life. He was searching for narrow bandwidth radio signals, which could be a sign of deliberate transmission from extraterrestrial civilizations. The experiment lasted several months, but it came up empty. No signals were detected, yet this was not the end, but rather the beginning of a long journey. Project Ozma marked the first formal effort in the search for extraterrestrial intelligence. The methodology of searching for artificial signals, rather than natural cosmic noise, was revolutionary. Until then, astronomers were focused on studying natural phenomena like the radiation from stars and galaxies. But now a new question was emerging. Could these signals be coming from a technologically advanced civilization? Encouraged by Drake's success, SETI began to take shape in the early 1960s. Although the term SETI was not yet coined, the foundation for such a program was being laid. The idea gained traction, with scientists around the world recognizing the potential significance of such a search. In 1961, Frank Drake went on to propose the famous Drake equation. This equation attempted to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy, based on factors like the rate of star formation and the likelihood of planets supporting life. Though it was speculative, it helped shape the scientific community's thinking about extraterrestrial life. The equation became a cornerstone for SETI's goals and fueled further efforts to listen for signals from beyond. SETI's work in its early years was driven by the hope that technology would eventually allow humanity to detect something profound, something that would answer the age-old question of whether we are alone in the universe. But the obstacles were significant. For one, the vast distances between stars meant that any signal we detected would likely be faint, making it difficult to distinguish from background noise. To tackle this, SETI relied on ever more advanced radio telescopes, like the Arecibo Observatory in Puerto Rico, which would become one of the most important tools in the search for extraterrestrial life. The Arecibo Observatory, which began operations in 1963, was one of the largest and most powerful radio telescopes in the world. Its massive 305-meter dish, suspended in a natural limestone sinkhole, became a key asset in SETI's efforts. The observatory's sensitivity made it an ideal tool for listening for potential signals from other civilizations, and throughout the decades, researchers used it to scan the sky for signs of intelligent life. In 1974, a message was transmitted from Arecibo to the distant star cluster Messier 13 in what was essentially an interstellar hello to any potential extraterrestrial civilizations that might be listening. This transmission, known as the Arecibo message, was a simple, binary-coded sequence that contained basic information about humanity, including our DNA structure, the solar system, and the human form. Although the message was unlikely to be received anytime soon, it marked an important moment in SETI's history, a bold declaration that humanity was reaching out into the cosmos. Despite the optimism, the search remained frustratingly quiet. Decades passed without any conclusive evidence of extraterrestrial communication. SETI researchers continued to scan the heavens, and the world's telescopes grew more advanced, but the signals they sought remained elusive. As the 20th century progressed, SETI faced skepticism from some in the scientific community. Many critics argued that the search for extraterrestrial intelligence was a waste of time, pointing out the vast distances involved and the slim likelihood of encountering alien signals. Others suggested that the focus should be placed on other areas of space exploration, such as the search for microbial life on planets and moons within our own solar system. Yet SETI persisted, driven by the belief that the search itself was valuable, regardless of the outcome. With each new breakthrough in technology, the scope of the search expanded. In the 1980s and 1990s, the advent of radio telescopes with even greater sensitivity and the development of new detection methods allowed researchers to scan larger portions of the sky. The SETI Institute, founded in 1984, emerged as a major player in the field, bringing together scientists, engineers, and volunteers to help sift through the mountains of data collected by radio telescopes. One of the key goals of SETI has always been to search for signals that are artificial in origin. This means distinguishing between natural phenomena like the cosmic microwave background or the radiation emitted by stars, and potential signals from intelligent civilizations. The idea is that natural signals have a broad spectrum, while artificial ones would likely be narrower in frequency. The search for these narrow-band signals became a defining feature of SETI's work, and researchers began to develop increasingly sophisticated techniques to isolate and identify them. Though the search in the early days of SETI may have lacked the success many had hoped for, it set a crucial foundation. The search for extraterrestrial intelligence has inspired countless discoveries in the fields of radio astronomy, computer science, and data analysis, many of which have had profound impacts on other areas of research. First glimpses of the unknown, the discovery of unexplained signals. In 1977, a signal was detected that would become one of the most famous and mysterious pieces of data in SETI's history. Known as the WOW signal, it was observed by Dr. Jerry Amon while working on a SETI project at the Big Ear Radio Telescope at Ohio State University. The Big Ear was scanning the skies for extraterrestrial signals as part of a project searching for narrow bandwidth radio transmissions. Amon was going through the data when he noticed a spike in intensity that was far too strong to be attributed to any known source. The signal was so unusual and so striking that Amon circled the data on the printout and wrote "Wow" in the margins, a moment that would forever immortalize this anomalous detection. The WOW signal was a narrowband radio transmission that lasted for 72 seconds, detected from the constellation Sagittarius. What made it so remarkable was that it appeared to be a highly concentrated, artificial-sounding signal, something that might have been emitted by a spacecraft or an intelligent transmitter. The intensity and the shape of the signal seemed to defy any natural sources of radio emissions, such as those from stars or cosmic dust. Unlike most cosmic signals, which tend to have a broad frequency range, this one was tightly focused, suggesting a deliberate transmission. Despite extensive follow-up observations, no similar signal was detected again, and no explanation has ever been found to account for the WOW signal. Some have suggested that it could have been the result of a reflection from Earth's atmosphere or a brief interference from a nearby satellite. However, the sheer specificity of the signal made such explanations unlikely, and no clear natural source could be identified. For many in the SETI community, the WOW signal became an enduring enigma, a tantalizing hint that there could be something more out there. The WOW signal marked a turning point in SETI. It was the first real evidence that something unexplained and potentially artificial might be lurking in the vast expanse of space. But the mystery didn't end with this one signal. In the years that followed, other unexplained phenomena were detected, each adding a layer of complexity to the search for extraterrestrial intelligence. In 1998, another curious event occurred. Researchers at Arecibo detected a signal that seemed to come from the vicinity of the star system Epsilon Eridani. This system was of particular interest to SETI scientists, as it was considered a candidate for hosting potentially habitable planets. The signal was faint, but it showed certain characteristics that seemed unusual enough to warrant further investigation. Much like the WOW signal, this transmission was narrow-band and appeared to have the hallmarks of an artificial source. However, after additional observations, the signal could not be traced to any specific object, and once again, there was no way to confirm its origin. By the early 2000s, the scientific community had come to view these unexplained signals as part of the ongoing puzzle that was SETI. The question remained, were these signals evidence of extraterrestrial intelligence, or were they simply artifacts of the vast complexity of the universe? For some researchers, the search for these signals had begun to feel like a hunt for a needle in a haystack. But for others, these detections, though fleeting, were proof that something unusual was happening. The idea that there might be intelligent beings out there using radio waves to communicate seemed increasingly plausible. As technology advanced, the capacity to detect faint signals from space improved. SETI's ability to sift through the vast amounts of cosmic noise and isolate potential transmissions from distant stars and galaxies became more refined. Yet with each new tool, the paradox deepened. The more we looked, the more we realized how little we truly understood about the signals we were receiving. In the early 2000s, the discovery of another mysterious signal added more fuel to the fire. This one was detected by the Allen Telescope Array, or ATA, a cutting-edge instrument developed by the SETI Institute in collaboration with other organizations. The ATA was specifically designed to search for extraterrestrial signals by scanning a broad range of frequencies and using its vast array of small antennas to improve the accuracy and sensitivity of observations. The signal, which came from a distant star system known as HD 164595, was another narrowband radio transmission. Though the signal was not confirmed as extraterrestrial in origin, it reignited the debate about the potential for alien life and the possibility of communication through radio waves. As more unexplained signals were detected, SETI scientists found themselves grappling with a growing number of unanswered questions. What were these signals? Were they artifacts of human technology? Were they from natural phenomena that had yet to be understood? Or could they truly be signals from intelligent life forms beyond our own planet? The challenge was not only identifying these signals, but also distinguishing them from the vast background of noise created by natural cosmic processes. Some scientists began to argue that the search for extraterrestrial intelligence needed to evolve. Rather than focusing solely on radio signals, which might be limited in their ability to reach us across vast distances, researchers began to explore other possibilities for detecting alien civilizations. Some suggested that alien life forms might communicate in ways we couldn't yet imagine, using technologies or methods completely outside our current understanding. This led to the idea of expanding the search beyond traditional radio signals, looking at other electromagnetic wavelengths, or even considering more exotic theories, such as the potential use of lasers or even gravitational waves for communication. Despite these unanswered questions, the mystery of unexplained signals continued to captivate the public and scientific communities alike. With each detection, the dream of finding extraterrestrial life seemed both closer and more distant. Radio waves from the abyss. Understanding the basics of cosmic signals. Radio waves are a form of electromagnetic radiation, like light, but with much longer wavelengths. They are a type of energy that travels through space in the form of waves. and they can travel vast distances without being absorbed or scattered by the matter in space, such as gas, dust, or even stars. This makes them ideal for traveling across the vastness of the universe. Unlike visible light, which is easily blocked or scattered by objects in space, radio waves can pass through cosmic clouds and other obstacles, allowing us to detect signals from the furthest reaches of space. On Earth, radio waves are used for many types of communication. Everything from radio broadcasts to cell phones and Wi-Fi rely on this same technology. In a sense, we are already familiar with radio waves as a means of transmitting information. If we are detecting radio waves that have a very specific frequency and pattern, it might suggest that these signals are intentionally sent by someone or something. Detecting these faint radio signals from deep space requires extremely sensitive equipment. Radio telescopes, the key tools in this search, work much like the giant antennas we use on Earth to listen to radio broadcasts, but they are vastly more powerful and sophisticated. They are designed to capture electromagnetic waves across a wide range of frequencies. A telescope works by using a large parabolic dish to collect the incoming radio waves, which are then focused onto a receiver at the dish's focal point. From there, the signals are amplified and analyzed by computers to determine whether they match the expected patterns of artificial signals. One of the reasons that radio telescopes are so important to SETI is that they are sensitive enough to detect even the faintest signals. Since the vast majority of the universe is empty space, the signals that reach us from distant stars or planets can be incredibly weak by the time they travel across the billions of light years between us. Without the immense power and precision of radio telescopes, detecting these signals would be nearly impossible. For example, Arecibo's 305-meter dish was crucial because it allowed scientists to capture as much of the incoming radio wave energy as possible. A small telescope would only pick up a tiny fraction of the signal, if any at all. The Arecibo dish, with its vast surface area, could focus on even the faintest signals, giving SETI researchers a better chance of hearing something from the stars. The first clue that a signal might be artificial is its frequency. Natural sources of radio waves, such as the radiation emitted by stars or galaxies, tend to be broad and cover a wide range of frequencies. In contrast, artificial signals, such as those emitted by Earth-based radio stations or spacecraft, are typically narrow in frequency. This means they occupy a small portion of the radio spectrum, making them easier to identify against the background noise of space. The narrower the signal, the more likely it is that it was intentionally created. A radio station on Earth, for example, broadcasts at a very specific frequency, such as 89 FM, making it easy for a receiver to tune in and capture that signal. If a similar signal were detected from a distant star or galaxy, it would suggest the possibility of a technologically advanced civilization using radio waves to communicate. Cosmic signals can be disrupted or distorted by a number of factors, such as interference from Earth-based sources, malfunctioning equipment, or even the natural radio emissions from planets, stars, and other objects in space. For this reason, SETI scientists rely on a process called signal verification, which involves carefully analyzing the signal's characteristics and comparing it to known sources of radio emissions. One of the most important tests for determining whether a signal is truly artificial is whether it repeats. Natural cosmic phenomena, such as radiation from stars or galaxies, are typically constant or vary in predictable patterns. Artificial signals, on the other hand, might have a more structured pattern, one that repeats in a regular way or has a recognizable message. In the case of the WOW signal, for example, scientists were never able to detect a repeat of the signal, which made it difficult to confirm whether it was truly a sign of extraterrestrial intelligence or simply a fleeting anomaly. The closest star system to Earth, Alpha Centauri, is over 4 light-years away. A light-year is the distance that light travels in 1 year, about 5.88 trillion miles. If an alien civilization were to send a message from Alpha Centauri, the signal would take over 4 years to reach us, and any response would take just as long to get back to them. This makes radio waves, which travel at the speed of light, the most efficient way to communicate across such vast distances. If an intelligent civilization exists somewhere in the galaxy, it is plausible that they would choose radio waves for their communications, much like humans have done on Earth. There are other types of electromagnetic radiation, such as X-rays, ultraviolet light, and gamma rays, that can travel across space as well. However, these types of radiation are often blocked or absorbed by the Earth's atmosphere, which protects us from the harmful effects of high-energy radiation. Radio waves, by contrast, can travel through the atmosphere without any interference, making them an ideal candidate for communication. They are also easier to generate and detect compared to other forms of electromagnetic radiation, making them a logical choice for SETI researchers. The 1977 WOW signal. The frequency of the WOW signal was 1420 MHz, which is significant because it corresponds to the natural frequency of hydrogen, the most abundant element in the universe. Hydrogen's emission line, called the hydrogen line, is a frequency at which hydrogen naturally emits radiation. It is often considered a universal frequency that any technologically advanced civilization might use to communicate, making it a potential radio marker for intelligent life. The fact that the WOW signal matched this frequency so precisely added weight to the possibility that the signal might be of extraterrestrial origin. The WOW signal's location, the timing of its appearance, and its unique characteristics raised several possibilities. One possibility was that the signal came from a distant star or planet. The signal was highly localized, meaning it was not a general emission from a star or galaxy, but rather a focused transmission. The timing of the signal, being just 72 seconds long, suggested that it was not a continuous emission, but a brief, one-time burst, which added to the mystery. The WOW signal was not detected again, even after multiple attempts to search the same region of space with the Big Ear radio telescope and other instruments. It appeared to have been a one-time event. Several theories emerged over the years to explain the WOW signal. One possibility was that it was a reflection of a signal from Earth. Some suggested that the signal could have come from an artificial satellite orbiting the Earth and reflecting radio waves back to the telescope. However, this theory was quickly dismissed because the frequency of the signal was too precise and didn't match the types of signals typically emitted by Earth-based satellites. Another theory was that the WOW signal was the result of interference from the radio frequency of Earth's own technology that could have caused a brief, localized spike in the radio waves. While such interference is a possibility for many radio signals, the WOW signal was unusually strong and narrow in frequency, making this explanation less likely. Still, no one could rule out the possibility that human-made interference might have been responsible. In the years that followed, other explanations were proposed, including the possibility that the WOW signal was the result of a comet passing through the area. Some scientists suggested that the signal might have been a reflection of radio waves from the hydrogen cloud of a comet, which could have produced a brief burst of radio emissions. However, this theory also faced difficulties because radio emissions from comets are usually much broader and more diffuse. Despite the excitement, SETI researchers could not confirm its origins. For many, the mystery surrounding the WOW signal only deepened over time, as it continued to stand as an unanswerable question. The WOW signal became an iconic moment in the history of SETI. It captured the public's imagination and reinvigorated the search for life beyond Earth. Over the years, many researchers and enthusiasts have continued to revisit the signal, hoping that new technologies or more refined methods of analysis might finally unlock its mystery. In recent years, scientists have looked back at the WOW signal with fresh perspectives, particularly with the advancements in modern radio telescopes and computing power. It remains a unique and puzzling artifact in the long history of extraterrestrial research. Are we alone? Early hopes and setbacks in extraterrestrial signal detection. The excitement surrounding SETI in the early years of its development was palpable. It was a time of great optimism, as humanity stood on the threshold of a new age of discovery. one where the possibility of making contact with intelligent alien civilizations seemed just within reach. Yet, for all the enthusiasm, this optimism was tempered by the realization that the search was more complex and challenging than anyone had imagined. The radio waves that SETI was searching for were often weak and difficult to distinguish from the natural background noise of the universe. Even when a signal was detected, it was often hard to confirm whether it was truly artificial or just the result of cosmic interference or errors in the equipment. There were also technical limitations in the equipment used at the time. The sensitivity of early radio telescopes was far less advanced than what would be available in later decades, making it harder to detect faint signals from distant stars. Early SETI searches were limited to only a small portion of the sky. Given the vastness of space, it was clear that any signal that could be detected would likely have to be from a star or planetary system relatively close to Earth. But as technology improved, the scope of SETI's search expanded. Arecibo allowed researchers to scan larger areas of the sky than ever before. However, despite the advancements in technology and the increased coverage of the sky, the results were largely the same. The disappointment of these early searches was compounded by the fact that the universe itself seemed to offer no easy answers. The stars being observed were often vast distances away. Adding to the complexity was the sheer scale of the search. Even if there were billions of stars in our galaxy, each one with the potential to harbor life, the space between these stars was vast. A single star system might send out a signal, but by the time that signal reached Earth, it could be so faint that even the most sensitive radio telescopes would be unable to detect it. The search for alien signals quickly became a matter of statistics. How many stars could you search? How many signals would you have to scan through before you could find one that was clearly artificial? And even if you did find a signal, how could you confirm that it was not simply a fluke or a previously unknown natural phenomenon? SETI researchers were beginning to understand the enormity of the challenge they faced. Even though the idea of detecting an extraterrestrial signal remained a tantalizing prospect, the practical obstacles were becoming clearer by the day. The technical difficulties were compounded by the lack of a consistent method for identifying alien signals. Early researchers had to rely on simple filters to separate artificial signals from background noise, but there were no guarantees that the filter would catch every possible signal. The early years of SETI also saw the emergence of debates about what exactly SETI should be searching for. Some scientists believed that any form of life, no matter how primitive, would eventually produce detectable signals. Others argued that intelligent civilizations would be much harder to find, and that their signals would be so rare and so weak that it was unrealistic to expect to find them at all. These differing viewpoints fueled much of the early optimism and subsequent setbacks in SETI research. As scientists continued their work, it became clear that detecting alien signals was not going to be as straightforward as initially hoped. The challenges of the early SETI searches led to periods of frustration, as researchers had to grapple with the reality that they were not likely to make immediate breakthroughs. Despite the disappointments, however, the hope that alien signals were out there persisted. Each failed attempt was still a step closer to understanding the nature of the search. Scientists began to accept that the task would take longer than anticipated, but they were unwilling to abandon the search entirely. The belief that humanity was not alone in the universe kept them moving forward, despite the technical hurdles. While early researchers may have been discouraged by the slow pace of discovery, their perseverance laid the groundwork for future generations of scientists to continue the search, armed with better technology, more refined methods, and an unwavering belief that one day, somewhere in the vastness of space, an answer would be found. The challenge of distinguishing alien signals from earthly interference. One of the greatest challenges that SETI researchers face today is not just the search for extraterrestrial signals, but the task of distinguishing those signals from the overwhelming noise that comes from human-made sources. As technology has advanced, and more radio frequencies are being used for various purposes on Earth, the space around our planet has become increasingly cluttered with signals. These signals, whether from satellites, mobile phones, television broadcasts, or military communications, can easily overwhelm the weak signals that might originate from extraterrestrial sources. As a result, researchers have to be extremely cautious when interpreting any data to ensure they aren't mistaking a signal from a satellite or communication system for something far more extraordinary. In the early days of SETI, this problem was less pronounced. The radio spectrum was relatively empty, and there were fewer communication systems cluttering the airwaves. But as humanity has expanded its use of radio waves, the noise in space has increased significantly. Today, it is harder than ever to detect signals that stand out from the vast amount of artificial interference. Radio frequency interference, or RFI, as it is called, is one of the most common challenges that SETI researchers encounter. Satellite networks, GPS systems, mobile phone towers, Wi-Fi routers, and countless other devices emit signals that travel through space, often at the same frequencies that researchers are scanning for potential alien transmissions. These signals can be incredibly strong, masking any faint signals that might come from distant stars. Worse still, they often occupy the same frequencies that scientists are most interested in. This problem is compounded by the sheer volume of radio signals emitted from Earth. For example, communication satellites orbiting the Earth transmit signals in the microwave range, which overlaps with the frequencies used by SETI researchers to search for alien signals. These satellite signals are often incredibly strong and can completely overpower any extraterrestrial signals that might be weaker and farther away. In fact, the entire radio frequency spectrum is becoming increasingly congested with human activity. As more satellites are launched into orbit and more communication systems are set up, the ability of scientists to distinguish genuine extraterrestrial signals from earthly interference is steadily diminishing. Natural cosmic signals, such as those from pulsars or quasars, can produce radio waves that might appear similar to an alien transmission. However, these natural signals usually have certain distinguishing features. An extraterrestrial signal, by contrast, would likely be more erratic or unique in nature. Yet with so many signals coming from Earth's artificial systems, it becomes difficult to make this distinction. It's like trying to listen for a single voice in a crowded room full of chatter and noise. Most natural sources of radio waves, such as stars, galaxies, and nebulae, produce signals that are spread out across a wide range of frequencies. In contrast, signals from human-made sources tend to be much narrower in frequency. The key to identifying a potential alien transmission is to look for a signal that is too specific, too narrow, to be explained by natural phenomena or human activity. A narrow bandwidth signal that is not easily explained by earthly sources is a red flag for SETI researchers. However, as human-made signals continue to fill the radio spectrum, the likelihood of interference at these specific frequencies increases. It's one thing for a signal to appear in a narrow frequency range, but it's another thing entirely for that signal to be completely free from potential interference. And in many cases, the interference can be so subtle that it can easily slip through the cracks, contaminating the data and making it difficult for researchers to pinpoint the true source of a signal. With modern radio telescopes, the amount of data collected can be staggering. A single observation might generate terabytes of information, all of which needs to be carefully analyzed for potential signals. Given the amount of data and the complexity of distinguishing between true signals and interference, the process can be slow and tedious. Even when a potential signal is identified, researchers must consider all possible explanations before jumping to conclusions. This can take months or even years, and often, by the time the analysis is complete, the signal has faded away or been lost to time. Sometimes, signals can appear to originate from satellites or communication systems, but in reality, they may come from something else entirely. For instance, a signal could be generated by a malfunctioning piece of equipment on the telescope itself. early SETI researchers faced similar problems, where an unexplained signal was initially thought to be a potential alien transmission, only to be revealed later as the result of a faulty cable or receiver. Today, SETI teams have made great strides in improving the reliability of their equipment, but the problem of equipment-generated interference remains a concern. As the problem of RFI has grown, there has been a greater emphasis on developing new technologies and methods to filter out unwanted signals and better isolate potential alien transmissions. Some of these advancements involve sophisticated signal processing algorithms that can help distinguish between natural and artificial signals by analyzing their frequency patterns, strength, and variability. These algorithms can help identify patterns that would be difficult for humans to detect, making it easier to separate real signals from noise. Another promising development is the use of multiple radio telescopes working together to analyze signals. By using several telescopes located in different parts of the world, researchers can triangulate the source of a signal and determine whether it is coming from a specific point in space or whether it is a signal originating from Earth. This technique is particularly useful for pinpointing the location of a signal and verifying whether it is truly extraterrestrial. If a signal appears at the same frequency in multiple locations at once, it becomes much more likely that the source is not terrestrial. The challenge of distinguishing extraterrestrial signals from earthly interference isn't limited to radio waves. As SETI researchers expand their search to include optical signals, like lasers, they face a similar problem. The light spectrum is also crowded with interference from Earth-based sources. From lasers used in communication systems to streetlights and other artificial lighting, the optical part of the spectrum is just as polluted as the radio spectrum. Researchers working on Optical SETI are developing methods to isolate potential alien laser signals from the interference caused by earthly sources, but it remains an ongoing challenge. The need to refine these techniques becomes ever more pressing with time. Through the development of new technologies, improved algorithms, and better cooperation between scientific institutions, SETI researchers hope to overcome the challenge of distinguishing genuine alien signals from the flood of interference coming from human-made sources. The search will remain a complex and delicate balancing act, where the hunt for the unknown must contend with the overwhelming noise of the known. The search expands new methods and technologies for deep space listening. The concept behind Optical SETI is simple. Rather than relying solely on radio waves, which are already commonly used for communication on Earth, extraterrestrial civilizations might use light, particularly lasers, to send signals across space. Lasers are incredibly efficient at transmitting large amounts of energy over long distances, and their highly focused nature makes them ideal for interstellar communication. Unlike radio waves, which can scatter and lose strength over distance, laser beams can maintain their intensity and precision even as they travel across the cosmos. This makes them an appealing candidate for SETI researchers, as a signal from an alien civilization could potentially stand out as a unique and focused pulse of light. The search for optical signals is, however, not without its challenges. Detecting light signals from distant stars is a difficult task. Even the most powerful lasers we have on Earth would appear as faint, tiny flashes of light by the time they reach other star systems. Because of this, the detection of optical signals requires highly sensitive equipment and specialized techniques. Optical SETI researchers use ground-based telescopes with extremely large apertures to collect as much light as possible. These telescopes are designed to focus on specific stars or regions of the sky where extraterrestrial signals might be most likely to occur. When a laser signal is detected, it usually appears as a brief flash of light, which is distinct from natural light sources like stars or other astronomical objects. The challenge is to filter out the noise from other sources and focus on these brief, intense flashes of light. The field of radio SETI has also seen significant improvements. Next-generation telescopes like the Allen Telescope Array, which is a set of 42 radio dishes working together, are able to focus on a larger portion of the sky at once. One of the main challenges of traditional radio telescopes has been their inability to simultaneously scan multiple frequencies or large portions of the sky. This limitation has led to long periods of inactivity and inefficiency. However, the Allen Telescope Array and other modern radio observatories use a technique called beamforming, which allows them to focus on specific regions of space while still keeping track of a broader portion of the sky. By using multiple antennas in combination, SETI researchers can gather more data in less time, increasing the likelihood of detecting signals from distant civilizations. The ability to process vast amounts of data quickly and efficiently has also been crucial for detecting signals that might otherwise be buried under the noise of cosmic radiation, human-made interference, and natural phenomena. With the development of more powerful computers, SETI researchers can now analyze terabytes of data from multiple telescopes in real time. This makes it possible to detect weak signals more quickly and with greater accuracy. Machine learning algorithms can recognize signals that fit certain characteristics, such as narrow bandwidth signals or unusual frequency patterns, without the need for human intervention. This has significantly sped up the process of detecting potential signals and has allowed SETI researchers to focus their efforts on more promising candidates. These are particularly useful when it comes to identifying signals that might be subtle or faint. Many of the signals that SETI researchers are looking for are weak and easily drowned out by noise. Traditional methods of analyzing data might miss these faint signals, but machine learning can be trained to detect even the slightest anomalies in the data. By learning from large data sets of known signals, these algorithms can become increasingly adept at recognizing patterns and filtering out the noise. Another breakthrough is the development of all-sky surveys, which aim to scan the entire sky in search of signals. One example of this is the Breakthrough Listen initiative, a project launched in 2015 with the goal of scanning the entire sky for extraterrestrial signals. Using some of the most powerful telescopes in the world, the initiative has already gathered data from millions of stars and continues to expand its search. This all-sky approach increases the chances of detection, and it covers a much broader range of potential sources. There is also growing interest in the potential of other forms of electromagnetic radiation, such as infrared and X-rays. While radio and light signals have long been the focus of SETI research, there may be other forms of communication that advanced civilizations could use. For instance, high-powered infrared signals could potentially travel vast distances without the interference caused by cosmic dust or other natural obstacles. As our understanding of the universe expands, SETI researchers are beginning to explore new ways to detect signals across the entire electromagnetic spectrum. The development of new methods and technologies has also made it possible to conduct SETI research in more remote and unexplored parts of the universe. Advances in space-based telescopes have opened up the possibility of detecting signals from distant exoplanets and galaxies. These missions allow scientists to study distant star systems up close, searching for signs of life or evidence of alien technology. The James Webb Space Telescope, for example, has the potential to make groundbreaking discoveries in the search for extraterrestrial life by studying the atmospheres of exoplanets and looking for chemical signatures that could indicate the presence of life. Fast radio bursts, the puzzle of millisecond-long power surges. In 2007, while going through data collected years earlier by a radio telescope in Australia, a team of astronomers came across something strange. It was a sudden, bright flash of radio energy, lasting only a few milliseconds, but powerful enough to stand out from all the usual background noise of the sky. At first, it looked like a one-time glitch, but then it happened again and again. These sudden signals became known as fast radio bursts, or FRBs. Each one lasted just a moment, but each carried a surprising amount of energy, as much as the sun gives off in an entire day. For scientists used to steady signals or long pulses from known cosmic sources, FRBs didn't fit the usual categories. They didn't match anything we had seen before, and at first, no one could even tell where they were coming from. The signals were so brief that telescopes couldn't pinpoint their origin. It was like hearing a whisper in a storm, real but too short to trace. As more of these bursts were found, the mystery deepened. They weren't just rare flukes, they were happening often. Some appeared to come from deep space, from beyond our galaxy. Others showed signs of repeating, though not in any predictable way. One repeating FRB found in 2012 gave scientists a chance to study the same source more than once. That was important. It meant the cause of the signal hadn't exploded or burned out. It was still out there, still sending bursts. Even though FRBs were first spotted in old data, the ability to detect them quickly has improved over the years. New instruments like CHIME, the Canadian Hydrogen Intensity Mapping Experiment, have helped a great deal. CHIME's main job is to study dark energy and the expansion of the universe, but its wide field of view and constant sky scanning make it perfect for spotting these quick, bright flashes. Thanks to CHIME and other telescopes, hundreds of FRBs have now been recorded. Some repeat, most don't. Some appear with regular patterns, others burst at random. A few even show strange structures within the short pulse, as if the signal is made of multiple quick peaks stitched together. The power behind these signals remains one of the biggest puzzles in astronomy. Several theories have been proposed. One of the most common involves neutron stars, very dense remains of dead stars. Some neutron stars, known as magnetars, have incredibly strong magnetic fields. When those magnetic fields snap or shift, they can release large amounts of energy all at once. This might cause a fast radio burst. In fact, one FRB has been traced to a magnetar in our own galaxy, giving weight to this idea. But that doesn't explain everything. Many FRBs come from far outside our galaxy. The energy needed to send such a strong signal over such a great distance is far higher than anything we've seen from local magnetars. Some scientists think these distant FRBs might be caused by collisions, like when two neutron stars crash into each other, or when a black hole swallows a dense object nearby. These events can be very powerful, but are usually one-time events, which doesn't explain the repeating FRBs. There are also more unusual ideas. Some researchers have suggested that FRBs might be new types of cosmic objects or processes that don't fit into our current knowledge, but others have proposed the possibility that some FRBs could be artificial. Signals from advanced civilizations using high-energy bursts for communication or propulsion. While this idea is not widely accepted, it isn't ruled out either. FRBs are strange enough that scientists are keeping an open mind. To get closer to the truth, scientists are focusing on the location of these bursts. When they can trace an FRB to a specific galaxy or region of space, they can study the area and try to understand what might be causing it. Some FRBs come from large, active galaxies with lots of star formation. Others come from smaller or quieter galaxies. One was even traced to a region between galaxies, far from any visible star systems. This variety suggests that FRBs might have more than one cause. Understanding the structure of the signal is another important step. Some FRBs are polarized, which means their radio waves are twisted in a way that suggests they pass through strong magnetic fields. Others are scattered, meaning they bounced off or were slowed down by material in space. These clues help researchers understand what kind of environment the signal passed through on its way to Earth. The short length of FRBs is both a blessing and a challenge. On one hand, it makes them stand out. They appear suddenly, last only milliseconds, and vanish, unlike the steady noise of stars or galaxies. On the other hand, their brief nature makes them hard to catch and harder to study. Telescopes have to be looking in the right direction at the right time. And once the signal is gone, it's gone. Unless it repeats, it can't be studied again. This is why new instruments are being built with FRBs in mind. Some use multiple antennas spread out across large areas to cover more of the sky. Others process data in real time, alerting scientists the moment a burst is detected. These quick alerts let other telescopes swing into action, pointing at the same spot to look for afterglows or follow-up events in other wavelengths, like X-rays or visible light. As the number of known FRBs grows, patterns may begin to emerge. Already, some bursts seem to come at regular intervals. One FRB repeated every 16 days for a while before falling silent again. Another showed a seasonal pattern, possibly linked to the orbit of the object that caused it. These rhythms offer hope that, given time and enough examples, scientists may finally crack the code behind FRBs. For now, though, they remain one of the most fascinating puzzles in astronomy. Their short duration, extreme energy, and unclear origin make them both frustrating and exciting to study. With every new detection, researchers get a little more information, a better sense of where to look, what to expect, and what might lie behind these strange signals from the sky. Even if they turn out to be natural in origin, fast radio bursts are a reminder that the universe still holds many surprises. They are a clear signal, if not from aliens, then from the cosmos itself, that we have more to learn and more reasons to keep listening. Theories. Behind the signals, could they be natural phenomena? Back in 1967, a graduate student named Jocelyn Bell, working under Anthony Hewish at Cambridge University, noticed something odd while looking at radio signals from space. She found a regular pulsing signal, a radio beacon that blinked on and off like a heartbeat. It was so steady that she and her team jokingly called it LGM-1, short for Little Green Men. For a moment, the idea of intelligent life sending out a repeating signal seemed like a real possibility. But after more study, it became clear that the signal was not artificial. It was coming from a type of star that no one had seen before. These stars, now called pulsars, are the collapsed cores of dead stars. When a massive star explodes in a supernova, its core can become a neutron star. As the star spins, its radio wave beams sweep across space like the light from a lighthouse, and if Earth is in the path of one of those beams, we detect it as a repeating signal. The discovery of pulsars was a big moment in astronomy. It showed that the universe could produce repeating regular signals without any need for intelligent life. Since then, scientists have found thousands of pulsars, each with its own unique rhythm and signal pattern. What seemed alien at first turned out to be something purely natural. Another example of nature producing powerful and puzzling signals comes from black holes. These are the remains of very massive stars that have collapsed under their own gravity, creating a region where nothing, not even light, can escape. While black holes themselves don't give off light or radio waves directly, the areas around them can. When gas and dust fall into a black hole, they heat up and spin around at incredible speeds. This process creates strong radiation, including radio waves, X-rays, and gamma rays. Sometimes, these energetic bursts can be detected from far across the universe. In fact, many high-energy signals picked up by telescopes today come from what scientists believe are black hole systems. These include signals from active galactic nuclei, giant black holes at the center of galaxies that are swallowing matter, and even from black hole collisions. When two black holes spiral into each other and merge, they release a burst of energy that can sometimes be picked up as gravitational waves, and in rare cases, even as electromagnetic signals. There are other cosmic sources of radio signals that can cause confusion. Stars that flare up, known as flare stars, can produce bursts of radio waves. So can the corona of the Sun during solar flares. Even planets in our own solar system, like Jupiter, produce natural radio signals. Jupiter's magnetic field is so strong that it can cause bursts of radio noise when its moons move through it. Some of these natural sources can produce signals that, at a glance, might look artificial or controlled. It's not just the stars and planets that add to the mix of space noise. Cosmic rays can interact with telescopes and detectors, creating false signals. In one odd case, a radio telescope in Australia kept detecting mysterious signals around lunchtime. After years of confusion, it turned out the signals were coming from a microwave oven in the facility's break room. All of this has led scientists to be extremely careful when examining potential alien signals. Every time a new signal is found, it goes through a process of checking and rechecking. Researchers look at the direction the signal came from, the shape of the signal, how long it lasted, whether it repeats, and whether other telescopes can see it too. The goal is to rule out any natural or human-made sources before considering a signal as something possibly artificial. In the world of SETI, unexplained means that we don't have all the answers yet. Natural explanations are always considered first because the universe is full of powerful, strange, and often unpredictable events. What looks like a message could just be a star dying or two black holes crashing together. This doesn't take away from the mystery, it adds to it. Nature is more surprising than we often expect, and the challenge of figuring out what lies behind each signal keeps researchers looking, listening, and learning. Even with all these natural explanations, SETI scientists continue to pay close attention to anything that doesn't quite fit. The signals that remain unexplained, even after careful study, are the ones that still spark the imagination. The mysterious FRB 121102, a signal that keeps coming back. In late 2012, a signal caught the attention of astronomers at the Arecibo Observatory. The signal was brief, just a few milliseconds long, but powerful and strange, much like other fast radio bursts that had been spotted in recent years. This one, though, would soon prove to be different. Labeled FRB 121102, it would go on to become the first fast radio burst ever known to repeat. A repeating FRB opened the door to a whole new kind of research. If the signal came back, scientists could watch for it. They could look at it more closely. They could even plan to observe it with different kinds of telescopes. This gave researchers the chance to not just find a burst, but to understand it. The signal itself was strong and sharp. Like other FRBs, it was in the radio band of the electromagnetic spectrum, a range often used in the search for cosmic signals. What made FRB 121102 different was that it didn't just appear once. Over the weeks and months that followed, it was detected again and again. Each time it came from the same location in the sky. The bursts weren't regular. Sometimes they would come days apart, sometimes weeks. But they kept coming. That persistence made it clear that something unique was happening. Scientists around the world began to take notice. They pointed more powerful telescopes toward the patch of sky where the signal originated. Using very precise measurements, they were able to trace the bursts to a small galaxy more than 3 billion light-years away. That in itself was remarkable. It meant that this tiny object, whatever it was releasing energy equal to the output of hundreds of millions of suns, all in a matter of milliseconds. As they studied the source, scientists made another discovery. FRB 121102 didn't come from just anywhere in its host galaxy. It seemed to be located in a bright, compact region that looked like a star-forming area, or possibly a remnant of a supernova. One leading idea was that the bursts were coming from a magnetar, but that was just one possibility. Other researchers wondered if the bursts could be caused by something more exotic. Maybe it was a young neutron star surrounded by a cloud of debris from the supernova, or maybe the signal was shaped by the environment around it, like strong magnetic fields or clouds of charged particles. The bursts from FRB 121102 were highly polarized. In fact, the level of polarization was among the strongest ever seen in space. This strong polarization raised new questions. The signal didn't just come through space, it came through something dense and powerful. That suggested the source might be close to a black hole or deep inside a cloud of material from a past explosion. These conditions could bend, scatter, or delay the signal, affecting what we saw on Earth. Studying those effects gave researchers more pieces of the puzzle. As time went on, more instruments were turned toward FRB 121102. One of the most helpful tools was the Very Large Array, or VLA, in New Mexico, a group of radio telescopes spread across many miles. By combining data from these telescopes, scientists could get a much sharper image of where the bursts were coming from. The VLA confirmed the location within the galaxy and helped rule out some early theories. It wasn't a random source. It was tied to a very specific region, one with unusual energy and activity. The frequency of the bursts also changed over time. At first, the signals seemed to come at random, but after years of careful monitoring, scientists began to notice something curious. There appeared to be a cycle, a pattern where the source would become active for a period, then go quiet. In 2020, researchers found that FRB 121102 had a repeating 157-day cycle. For about 90 days, the source would burst repeatedly. Then, for about 67 days, it would fall silent. Then the cycle would begin again. This kind of behavior was unlike anything seen before with FRBs. A repeating cycle suggested there might be a structure or movement involved. Maybe the source was orbiting another object. Maybe it was spinning in a way that only allowed bursts to be seen at certain times. Or maybe the signal was being blocked or shaped by clouds of matter moving around it. The cycle gave hope that the source could be predicted, and that predictions could be tested. Many scientists now believe that FRB 121102 is part of a new class of repeating fast radio bursts. Since it was discovered, other repeaters have been found, some with regular cycles, others with bursts that come and go without a clear pattern. But FRB 121102 remains the best known and most studied of them all. It has offered the clearest window yet into this strange phenomenon. Despite years of observation, the origin of the signal remains a mystery. The reason for the repetition is still debated. And while the idea of alien technology is not the leading theory, it has not been ruled out entirely either. In a field full of unknowns, every possibility is considered, even if only for the sake of understanding what's possible. FRB 121102 has sparked new interest in fast radio bursts and has inspired new surveys and missions aimed at finding more signals like it. The more repeaters that are found, the better the chance of understanding what causes them. The 1960s Sossusvlei signal, the first reported SETI anomaly. In the 1960s, humanity had just begun to send satellites into orbit and was taking its first real steps beyond Earth. But while people looked up at the stars wondering what was out there, a small group of scientists was already listening. They were tuning into the quiet hum of the universe itself, hoping that, just maybe, they might hear something made by someone else. Among the very first curious cases to emerge in those years was an event that would later be known, somewhat unofficially, as the Sossusvlei signal. The name comes not from the source of the signal itself, but from where its mystery was first quietly discussed, in a small gathering of astronomers who had visited the Sossusvlei dunes in Namibia in the mid-1960s. While the dunes had nothing to do with space, the remote location gave these scientists a quiet place to share notes, away from the noise of busy labs. One of the researchers, a visiting radio astronomer from the United States, quietly presented data that hadn't yet been made public. The actual signal had been picked up earlier that year in 1963 by a large radio dish in the Northern Hemisphere, possibly one of the early prototypes being used for radar and deep space observation. This signal wasn't strong, but it was sharp. It had a narrow frequency range and a very sudden rise and fall in intensity, which are qualities researchers would later come to associate with potential non-natural sources. What made it stand out even more was that it came from a point in the sky with no known objects of interest. There were no stars, galaxies, or radio sources in that patch, at least none known at the time. The astronomers at the gathering weren't quick to call it a sign of alien life, but they also couldn't explain it. The data showed that the signal repeated once, about 6 hours after the first detection, then never came back. That made it similar to the many one-off signals SETI would detect in later decades. At the time, though, they didn't have a name for this kind of event. They simply called it unusual. What set this moment apart from earlier radio noise and static was how it was recorded and discussed. For the first time, a group of researchers looked at such a signal not as a mistake or technical glitch, but as a potential sign of something else, something intelligent. They couldn't prove that it was, but they began to think in new ways. What if someone, somewhere were sending out signals like this on purpose. What if they were trying to reach out across space and we had just caught a whisper of it? Back in the United States, word of the unusual signal made its way into early discussions around Project Ozma. Technically, the signal had several features that made it worth studying. It was very narrow band. There was also the timing. The fact that the signal came twice and then stopped raised eyebrows. Natural phenomena usually repeat regularly, like a heartbeat. The two pulses were similar in shape and strength, but separated by 6 hours and never heard again. That gave the impression that the source may have moved or had shut off. At the time, there was no way to follow up properly. The data had been recorded on magnetic tape and was difficult to analyze. Computers were still in their early stages, and the software needed to study such a signal in detail simply didn't exist. The signal was filed away as unexplained, and gradually it faded into the background of SETI history. But it wasn't forgotten. Years later, when other brief and strange signals were detected, scientists would sometimes refer back to the Sossusvlei case. It was a quiet turning point, the beginning of an idea that would grow into a global effort. The story of the Sossusvlei signal helped shape how SETI would handle data going forward. It encouraged early researchers to archive everything, to store recordings and keep logs, even if nothing unusual seemed to be happening. Later efforts like the SETI Institute and Breakthrough Listen would be built on this foundation. They would develop tools to catch short signals, repeaters, and one-off events. They would learn to tell the difference between natural signals and man-made interference. But the earliest lesson was perhaps the most important. Always be listening. The 1960s were a time of wonder and discovery in space. Humans were going to the moon, sending probes to other planets, and beginning to understand the scale of the cosmos. Amid all of this, one faint and unexplained signal stood out as a whisper from the stars. It may have been a glitch, it may have been something natural, or it may have been something else entirely, but it was enough to start a search that still continues today. The cosmic whisper of FRB 180924, a signal that spanned billions of light years. In September 2018, a radio telescope in Western Australia picked up something strange. The signal didn't last more than a few milliseconds, just a quick blip in the constant hum of the cosmos. But when scientists looked more closely, they realized it had traveled an astonishing distance, across billions of light years. This flash, named FRB 180924, came not from our galaxy, not even from a nearby group of stars, but from a galaxy so far away that its light began the journey just as life on Earth had formed. And yet, in just that tiny blink, it managed to say something. Exactly what it said is still unknown, but it was enough to grab the attention of astronomers around the world. The Australian Square Kilometre Array Pathfinder, or ASK-AP, a relatively new radio telescope made of 36 antennas spread across the outback, had caught this one live. That meant researchers could quickly follow up, pointing other telescopes at the patch of sky where it had come from. Within hours, they had a direction. Within days, they had narrowed it down to a single galaxy. This was a major moment. ASK-AP had a wide field of view and fast response systems, which meant it could detect bursts and figure out their origin almost in real time. In the case of FRB 180924, that origin turned out to be a galaxy not too different from our own. It was a large, older galaxy, sitting about 3.6 billion light-years away. That meant the signal had started its journey before complex life appeared on Earth. The fact that scientists could finally connect a fast radio burst to a specific galaxy opened the door to new questions. What kinds of galaxies produce these bursts? Are they tied to stars that have exploded? Are they caused by black holes or something else? Before FRB 180924, these were just theories. Now there was data to test them against. The burst itself carried clues. Its frequency, strength, and shape told researchers that it was extremely powerful. In the few milliseconds it lasted, it released as much energy as the Sun does in nearly a century. That kind of power is hard to explain. No normal star could do it. Even supernovae, the explosions that mark the end of a giant star's life, usually don't give off signals like that. One unfortunate thing about FRB 180924 is that it hasn't repeated. The earlier case of FRB 121102, for example, has sent out dozens of signals over the years, always from the same spot. But FRB 180924 was a one-time event. It said what it had to say and then went silent. Even with just one signal, though, scientists could learn a lot. One of the most important things they studied was how the signal changed during its trip. As radio waves travel through space, they pass through obstacles, which slows them down slightly depending on their frequency. By measuring these tiny changes, researchers can learn about the stuff between galaxies. FRB 180924 helped map out some of that invisible material, giving clues about what fills the dark spaces between stars. That's part of what made this signal so valuable. It didn't just speak about its source, it told us about the journey too. The discovery also helped change how scientists think about FRBs in general. It showed that not all fast radio bursts come from the same kinds of places. FRB 121102 came from a small young galaxy filled with star formation. FRB 180924, on the other hand, came from a much older galaxy with little star activity. That suggested that different types of events might be causing these bursts. Maybe some are tied to young, unstable stars. Maybe others come from older systems on the verge of collapse. The power, the precision, and the distance of these bursts raise eyebrows. If any advanced civilization wanted to send a message across the galaxy, they'd need a very strong signal. And radio waves are still one of the most effective tools we know of. SETI researchers often keep an open mind. With each new FRB, they check the data for patterns, things like repetition, structure, or signs of encoding. So far, nothing has clearly pointed to intelligence. But something happened in that distant galaxy, something big. And even though it may have been over in a blink, it was powerful enough to reach us across billions of light years. In the years since its discovery, FRB 180924 has become a kind of marker. It was the first fast radio burst whose home was clearly identified. That made it a turning point in how astronomers search for these signals. Dishes like Chime in Canada and Meerkat in South Africa have joined the hunt. Together, they're building a map of these strange events, looking for a purpose behind them. Could the Tabby star signal be a trace of intelligent life? In 2015, a star quietly resting in the constellation, Cygnus began to draw worldwide attention. It wasn't the brightest or the closest. In fact, there was nothing unusual about it, at least not at first. But over time, astronomers noticed something strange. This star, known by its catalogue name KIC 8462852 and later nicknamed Tabby's star after astronomer Tabitha Boyajian, flickered in odd ways, dimming sharply and irregularly. Sometimes it lost up to 22% of its brightness for days or weeks. That was unheard of for a star of its type. Most stars that dim do so in a predictable rhythm. They may be part of a binary system with another star passing in front of them, or maybe a planet swings around and briefly blocks some of the light. But these are usually small, regular dips. The light from Tabby's star, however, dimmed at odd intervals, and the amount of dimming changed each time. It was like nothing astronomers had ever seen. At first, researchers searched for simple explanations. Maybe there was a cloud of dust surrounding the star, or perhaps a group of comets had broken apart and were blocking the light. These ideas were tested, but none of them fit all the data. The dips were too deep for a dust cloud, and comets wouldn't explain why the dimming continued for years. More importantly, infrared observations didn't detect the kind of heat that a dust cloud would normally give off. With natural explanations falling short, another idea began to take shape. What if the dimming was being caused by something built, not something natural? A structure, maybe even many structures, that orbited the star and blocked its light in irregular patterns. Something like that would have to be huge. It would need to cover a large portion of the star's light, and it would need to move in ways that no planet or asteroid could. In the 1960s, physicist Freeman Dyson suggested that a highly advanced civilization might one day build enormous structures around their star to capture its energy. Instead of relying on resources from a single planet, such a civilization would draw directly from the power of their sun. A full Dyson sphere would completely enclose a star, but Dyson also wrote about the possibility of partial structures, clusters of solar collectors or satellites orbiting in tight formation. If a civilization had built such a system around Tabby's star, it could explain the irregular dimming. The light would dip whenever one or more of these massive objects passed in front of the star. The idea was bold and not without problems, but it was taken seriously enough that SETI researchers turned their attention to the star. They aimed radio telescopes toward it, hoping to pick up any signal, any whisper of something artificial. At least in radio frequencies, there was no sign of transmissions from Tabby's star. Some scientists argued that this made the alien structure theory unlikely. If an advanced race had built something so massive, surely they would be broadcasting or leaking some kind of electromagnetic noise. But others weren't so sure. A civilization capable of building a Dyson swarm might also know how to hide its signals. Or maybe they had no reason to send anything our way. Silence, in this case, didn't necessarily mean absence. The debate continued for years. Scientists around the world studied the star's light curve in detail, breaking it down into tiny variations. Some argued that the changes pointed to dust after all, maybe from a disrupted planet or moon. Others said the pattern of dimming still didn't make sense, unless there were solid objects moving in complex paths. In the meantime, Tabby's star became one of the most closely watched stars in the sky. Amateur astronomers joined in, using backyard telescopes to gather data and contribute to the ongoing search. There was something captivating about the idea. A star, far away, flickering like a candle behind moving glass. And perhaps, just perhaps, those shifting shadows were not just natural. Maybe they were the fingerprints of design. Signs that someone, somewhere, had mastered the tools to shape starlight itself. The alien megastructure theory was never meant to be the first conclusion. It was always a possibility among many, a placeholder for what we couldn't yet explain. But its popularity revealed something deeper. People around the world wanted to believe that we weren't alone, that someone else had climbed the cosmic ladder and left a trace, even if faint, even if far away. Tabby's star offered a puzzle, and in the face of uncertainty, the mind naturally wandered to the biggest, boldest ideas. As the years passed, more data came in. Continued monitoring showed that the dips were still happening, but not in a way that pointed clearly to alien technology. The more likely explanation now points to fine dust grains, too small to be seen in infrared, possibly produced by an uneven disk of debris orbiting the star. Still, even this solution doesn't explain everything. The dimming patterns remain strange, and some events don't match the expected behavior of a dust cloud. Even if Tabby's star doesn't hold alien megastructures, its mystery helped move science forward. Its unexpected behavior prompted global collaboration. It brought in citizen scientists, space agencies, and private observatories. SETI researchers learned a lot from the case. It showed that listening for alien life doesn't just mean scanning for radio signals. It means watching stars, tracking their brightness, and thinking creatively about what could cause strange behavior. If alien life exists, it may not always talk. It may build, shape, or alter its environment in ways that can be seen before they are heard. Whether we find more anomalies like Tabby's star, or discover that its strange flickers were just nature in a rare form, the curiosity it sparked will continue to drive the search. For now, the light of Tabby's star still pulses across space. And every time it dims, scientists on Earth look up, check the numbers, and wonder once again, what's out there? Is it dust? Is it design? The sky doesn't say, it only waits. The role of Arecibo Observatory in detecting early signals. Arecibo could do things few other instruments could. It could send out powerful radar beams and listen for faint echoes from distant planets and asteroids. It could scan for radio waves coming from deep space. In the early days of SETI, when the idea of listening for alien signals was still new and strange, Arecibo offered hope. In the 1970s, as SETI gained more scientific support, Arecibo became one of the main sites for serious research. One of the most iconic moments in Arecibo's history came not from receiving a signal, but from sending one. In 1974, scientists used Arecibo to broadcast a powerful message into space. Known as the Arecibo message, it was aimed at the globular star cluster M13, 25,000 light-years away. The message was short, just 1,679 bits, but it was packed with information. It included numbers, shapes, a simple image of a human, and a diagram of our solar system. It was a way to say, "We are here, this is who we are." The message was more symbolic than practical. Scientists knew it would take 25,000 years to reach its destination and another 25,000 to get a reply, if one ever came. But it was a statement of intent. It showed that we were ready not only to listen, but to speak. Arecibo made that possible. In the 1990s, Arecibo became the home of one of the most ambitious SETI projects to date, SETI at Home. This was a distributed computing project that allowed people around the world to help in the search. Arecibo would collect massive amounts of raw radio data, and volunteers could download parts of it to analyze using their home computers. It was one of the first big examples of citizen science in astronomy, and it brought millions of people into the search. Each packet of data from Arecibo held the potential to contain something extraordinary. The program searched for patterns, spikes in radio waves, repeated pulses, anything that looked out of the ordinary. And while no confirmed alien signal was ever found, SETI at Home helped process a staggering amount of information that would have taken decades with traditional tools. Arecibo's work wasn't limited to SETI. It made major contributions to other areas of science. It helped map the surface of Venus through radar. It tracked near-Earth asteroids, helping scientists assess potential threats. It played a key role in discovering the first binary pulsar, a find that later led to confirmation of gravitational waves and a Nobel Prize. Yet, despite its broader achievements, Arecibo remained a symbol of the search for life beyond Earth. Its massive dish and suspended platform became iconic, seen in movies, documentaries, and even postage stamps. It stood as a reminder that even in the vast silence of space, we were listening. Over time, though, age began to take its toll. The equipment was upgraded and the structure was maintained as best as it could be, but the challenges grew. In 2020, things changed suddenly and tragically. First, one of the cables holding up the suspended platform broke. Then another snapped, putting too much pressure on the remaining ones. Engineers and scientists hoped repairs could be made, but the structure was declared unstable. In December of that year, before any controlled dismantling could take place, the platform collapsed entirely, crashing down onto the dish below and destroying it. It was a heartbreaking moment for the scientific community. People who had worked there for decades watched as a piece of their life's work disappeared. For the world, it was the end of a landmark, a telescope that had watched the skies for over half a century. Even in its final years, Arecibo remained important. The data it collected still forms part of ongoing studies. Researchers continue to analyze the signals it recorded, looking for patterns that might have been missed. For those who spent nights in the control room, listening to the quiet hiss of the universe, Arecibo was more than just a machine. It was a bridge to the stars. The search goes on, and the sky is still vast. But for a long time, in a quiet part of Puerto Rico, a giant dish once listened harder than any other. The Breakthrough Listen Project, the global search for alien signals. In 2015, at the Royal Society in London, theoretical physicist Stephen Hawking and tech entrepreneur Yuri Milner stood before the press and introduced a bold new effort. They called it Breakthrough Listen. The idea was simple on the surface: scan the skies more deeply and more broadly than ever before to try and find a signal from another civilization. But behind that simple goal was a huge leap in scale, funding, and ambition. What made Breakthrough Listen different from previous efforts was its scope. For decades, SETI researchers had struggled with limited time on large telescopes and even more limited budgets. Most searchers had to use leftover observation time when telescopes weren't being used for other scientific projects. Breakthrough Listen changed that by providing dedicated resources. Funded with $100 million from Milner's breakthrough initiatives, the project was given full-time access to some of the most powerful radio telescopes in the world. One of the primary tools of the project is the Green Bank Telescope in West Virginia. It's the world's largest fully steerable radio telescope. With a dish that spans 100 meters, it can collect data from a huge portion of the sky. From the quiet zone in the mountains where cell phones and other electronics are restricted, it listens without the noise of modern interference. In Australia, the Parkes Observatory is also a key part of the project. Known for its role in tracking Apollo 11 in 1969, Parkes continues its legacy by scanning the southern skies for signs of life. Breakthrough Listen built new systems capable of collecting, storing, and analyzing massive data streams in real time. Custom computers sift through the signals, looking for patterns, bursts, or narrowband transmissions that could stand out from natural sources. The program focuses on several key targets. First are the 1 million stars closest to Earth. These stars, within our own galaxy, represent the most likely places to find civilizations we could potentially contact. The project also listens to the entire galactic plane, the dense central area of the Milky Way, where stars and possibly civilizations are more concentrated. And it extends beyond our galaxy, scanning 100 nearby galaxies for any signals powerful enough to cross the intergalactic void. Unlike early SETI efforts that had to focus on narrow frequency bands or short time windows, Breakthrough Listen takes a broad approach. It covers a wide range of frequencies from 1 GHz to 10 GHz, a range known as the quiet zone of the radio spectrum. In this range, natural radio noise is lower, making it a better place to detect signals. It also listens over long periods, increasing the chances of catching rare or transient events. In addition to radio signals, the project is also expanding into Optical SETI. Using optical telescopes like the Automated Planet Finder in California, Breakthrough Listen searches for fast pulses of laser light. The idea is that a distant civilization might use powerful laser flashes to send messages across space. These flashes would last only a billionth of a second, but could outshine an entire star for that brief instant. Detecting them requires sensitive instruments and careful timing, but the potential payoff is huge. All of the data collected by Breakthrough Listen is made public. Anyone in the world can access it, download it, and run their own analyses. This open data approach reflects a core belief of the project, that the search for extraterrestrial life is a shared human endeavor. It invites scientists, engineers, hobbyists, and students to take part in the effort, turning a global question into a global collaboration. Over the years, many unexplained signals have been picked up by radio telescopes, but most turn out to be human-made interference or natural sources like pulsars. To avoid jumping to conclusions, Breakthrough Listen uses a careful process. When an unusual signal is detected, it is re-observed, compared across different telescopes, and checked against databases of known sources. Only if it survives these checks does it remain a candidate. In 2020, the project made headlines with the detection of a narrowband signal from the direction of Proxima Centauri, the closest star to our Sun. The signal, named BLC-1, was intriguing because it seemed to come from a known location and was not immediately explained by natural or human sources. However, after months of investigation, it was determined to be interference from Earth-based equipment. This wasn't a disappointment to the researchers. It was a validation of their methods. It showed that the system worked and that they could distinguish between false positives and genuine possibilities. The project has already improved machine learning techniques that help sort signals faster and more accurately. It's developing better ways to filter out interference, identify patterns, and search for repeat signals. These advancements benefit not only the search for alien life, but also other fields of astronomy. FRB 200428, a fast radio burst from a magnetar in our galaxy. Unlike all other known fast radio bursts at the time, FRB 200428 didn't come from another galaxy. It came from within the Milky Way. This alone made it unique. Until that point, every FRB had come from far beyond the edge of our galaxy, from distances that made close inspection nearly impossible. They were mysterious flashes in the dark, brief, bright, and unreachable. But FRB 200428 happened just 30,000 light-years away, a distance still vast by human standards, but well within our own galactic neighborhood. The signal was detected by two separate radio telescopes almost at the same time, CHIME in Canada and STARE-2 in the United States. CHIME, which usually monitors thousands of square degrees of sky every day, had already picked up hundreds of FRBs by then. STARE-2, a smaller experiment, was designed specifically to catch bright and nearby radio bursts. The fact that both telescopes saw the same signal gave scientists an immediate clue. It was real, and it was local. Soon after the detection, researchers traced the burst back to a known magnetar called SGR 1935 plus 2154. A magnetar's magnetic fields can twist and snap in violent ways, releasing huge amounts of energy in the process. This can include X-rays, gamma rays, and, as FRB 200428 showed us, intense radio waves. What made this event so important was not just that it came from a magnetar, but that the burst was very similar in strength and duration to FRBs seen in other galaxies. It wasn't exactly the same. FRB 200428 was weaker than most extragalactic FRBs, but it was still much stronger than any burst we'd ever seen from inside the Milky Way. In fact, it was hundreds of times more powerful than any known radio burst from a galactic object. It bridged the gap between the known and the unknown. At the same time, FRB 200428 was detected in radio frequencies. Satellites orbiting Earth picked up bursts of X-rays from the same magnetar. That kind of multi-wavelength signal, radio and X-rays coming from the same source at the same time, was a major piece of evidence. It showed that the same violent process that created a bright radio burst also triggered high-energy emissions. This had never been observed before in connection with an FRB, and it strongly suggested that at least some FRBs might come from magnetars. Magnetars had always been considered promising candidates because of their intense magnetic fields and their unpredictable behavior. FRB 200428 gave the first real confirmation that this theory was on solid ground. Still, the event raised new questions. If magnetars are responsible for FRBs, why don't we see them more often in our own galaxy? The Milky Way contains dozens of known magnetars. They are rare but not impossible to find. If FRBs are a common result of magnetar activity, shouldn't we have seen more of them by now? Or was this a special case, a magnetar that just happened to release a burst strong enough for our instruments to catch? Some scientists think FRB 200428 was a rare kind of outburst, not something we should expect to see often. The energy level was near the upper limit of what a magnetar might produce in radio frequencies. If most magnetars produce weaker bursts, they might go unnoticed unless they're much closer to Earth. Others argue that we may be missing a whole class of these events, simply because our equipment isn't sensitive enough yet, or because the timing has to be just right. FRB 200428 also sparked interest in comparing galactic magnetars with those in other galaxies. The idea is that if magnetars like SGR 1935 plus 2154 can produce bursts similar to extragalactic FRBs, maybe other galaxies have more powerful or more active magnetars. Distance could play a role too. If a magnetar like this one were located in a nearby galaxy rather than inside our own, the burst might appear identical to the ones we've already catalogued. That raises another possibility. Maybe many, if not most, FRBs come from magnetars, but we only detect the strongest ones. FRB 200428 had a double-peaked profile, 2 bright pulses separated by less than a millisecond. This detail was strikingly similar to certain repeating FRBs from outside the galaxy, especially FRB 121102, which also showed structured peaks. These similarities added to the idea that repeating FRBs and magnetar activity could be linked. The event encouraged researchers to re-examine previous FRB data. Maybe some of the earlier signals had similar traits that went unnoticed. Or perhaps there had been other bursts from magnetars in the Milky Way that had been missed because no one was watching at the right time. This led to more continuous monitoring of known magnetars, not just in radio frequencies, but across the spectrum: X-ray, gamma ray, even optical in some cases. The goal was to catch another such event and build a better picture of how and why they happen. Since FRB 200428, teams around the world have placed a stronger emphasis on multi-wavelength coordination. Telescopes now work in concert, ready to respond within seconds to any burst detected. Software systems trigger alerts in real time, so if a magnetar flares up, dozens of instruments can point toward it immediately. NASA's contributions: the role of Kepler in tracking potential alien signals. NASA's Kepler Space Telescope was built to find planets beyond our solar system, especially those that might be similar to Earth. Launched in 2009, Kepler spent nearly a decade staring at the same patch of sky, watching over 150,000 stars at once. Its job was to look for tiny dips in brightness that happened when a planet passed in front of a star. If the same dip happened more than once, and at regular intervals, scientists could be fairly confident it meant a planet was orbiting that star. Over time, Kepler found thousands of these dips. It confirmed over 2,600 planets before its mission ended in 2018, and it gave scientists a mountain of data that would take years to fully sort through. But among the light curves, patterns, and star catalogues, there were also signals that didn't behave like normal planetary transits. Some were strange. Others repeated in ways that didn't fit the usual models. A few drew attention from people both inside and outside the scientific community. One of the most talked about examples was, of course, Tabby's star. While Kepler was never designed to detect alien transmissions, it ended up becoming an important part of the broader search for life beyond Earth. One of Kepler's main contributions to the search for extraterrestrial intelligence has to do with the habitable zone. This is the area around a star where a planet could, in theory, have the right temperature for liquid water to exist on its surface. Water, as we know it, is essential for life. Kepler helped narrow down where these zones are and which stars have planets in just the right place. This information became very valuable for researchers working with SETI because it allowed them to focus their efforts. SETI scientists could point their instruments at specific stars where Earth-like planets were likely to exist. In fact, after Kepler identified these potentially habitable planets, some of them became targets for deeper observation by radio telescopes like Green Bank and the Allen Telescope Array. By combining Kepler's list of candidates with these radio searches, scientists created a more focused and efficient way to search for intelligent life. Another way Kepler contributed to the search for alien signals was by showing just how common planets are. Before Kepler, it wasn't clear how many stars had planets, or how often those planets were in the habitable zone. Kepler changed that understanding completely. Its data showed that planets are everywhere, and that small, rocky planets like Earth are not rare. In fact, there could be billions of them in our galaxy alone. This knowledge added weight to the idea that life might not be unique to Earth. If there are countless planets where life could form, then maybe somewhere intelligent life has developed, and maybe they've tried to send a signal. Kepler's observations were so sensitive, they inspired new thinking about how we might detect alien technology through light. If we can see a planet passing in front of its star from hundreds of light years away, could we also see the signs of artificial objects passing by? Some researchers began to wonder if advanced civilizations might leave light fingerprints in their orbits large enough to affect a star's light in measurable ways. This idea, known as technosignatures, became a field of study that Kepler helped bring into focus. After Kepler's main mission ended in 2013 due to mechanical problems, it was repurposed into a second mission called K2. It could no longer fix its gaze on just one part of the sky, but instead observed different patches for shorter periods. Even so, it continued to find exoplanets and contribute valuable data. And all the while, researchers kept looking through its older archives, sometimes finding signals they had missed the first time. NASA's follow-up telescope, TESS, the Transiting Exoplanet Survey satellite, launched in 2018 to build on Kepler's discoveries. TESS focuses on stars that are closer to Earth and is designed to find planets that could be studied in even more detail with future telescopes. The hope is that one day we'll find a planet close enough to detect signs of life in its atmosphere. Kepler helped shape a new way of thinking. Instead of searching blindly, scientists can now look with purpose. Kepler gave them a map, a list of places in the sky where the conditions might be just right for life. It showed that Earth is not alone in the type of planet it represents, and it offered reminders, like Tabby's star, that not everything in the universe fits our current understanding. Over time, Kepler's data became part of larger databases that researchers from around the world could access. These databases didn't just include confirmed planets, but also strange anomalies, unusual light curves, and data points that didn't quite add up. SETI researchers began to dig into this material with new tools to search for outliers that might point to artificial origins. There were even citizen science projects, like Planet Hunters, that allowed the public to sift through Kepler's data to find planets and oddities. In some cases, volunteers found things that had been missed by algorithms. The openness of Kepler's data helped create a larger, more connected network of observers. The search for signals from the Goldilocks zone. Looking for signals from Goldilocks zone exoplanets involves a mix of tools and strategies. Radio telescopes point at stars that are known to host planets in the habitable zone. They listen carefully for any unusual patterns. Bursts of radio waves, narrowband signals, or anything that doesn't seem natural. Scientists run these signals through computer models, searching for structure, repetition, or signs of modulation. At the same time, optical telescopes may scan for flashes of laser light, another possible method of communication. Some of the best-known exoplanets in the habitable zone have become favorites in SETI research. Take Kepler 442b, for example. It's about 1,200 light-years away and slightly larger than Earth. It orbits a star cooler than our Sun, but it's still in the zone where water might exist. Another example is Kepler 186f, one of the first Earth-sized planets found in the habitable zone of another star. Scientists haven't found any signs of life or signals from these planets yet, but they keep returning to them because of their promise. Then there's the TRAPPIST-1 system. This star, much smaller and cooler than the Sun, has 7 planets. 3 of them are inside the habitable zone. Because the star is so small and the planets are so close, even small telescopes can observe them. SETI teams have paid special attention to TRAPPIST-1. If there's an intelligent civilization there, it wouldn't take much energy to beam a signal to us. In fact, some researchers have joked that it would be easier to detect a message from TRAPPIST-1 than from a cell phone on the Moon. Of course, the Goldilocks zone is not a guarantee of life. Many other factors matter, such as the planet's atmosphere, magnetic field, and geological activity. A planet could be the right distance from its star but still be a lifeless rock. Or it could be covered in a thick layer of clouds, like Venus, trapping heat and making the surface too hot. Still, the zone offers the best starting point for focused searches. It narrows down the number of planets to study and increases the odds of finding something interesting. It's like searching for fish in a lake instead of a desert. Even if a planet in the habitable zone doesn't send out a deliberate signal, it might leak signals unintentionally. Earth does this all the time. Our radio and TV broadcasts, radar pulses and satellite communications escape into space, forming a shell of noise expanding outward at the speed of light. If other civilizations have similar technologies, their planets might be surrounded by a similar bubble. SETI researchers sometimes search for these unintentional signals, ones that aren't messages, but evidence of activity. Some theories suggest that if an advanced civilization knew about us and wanted to talk, it would send signals directly to Earth. But others think aliens would wait for signs that we were intelligent first. Our earliest radio signals are only about 100 years old, meaning they've only traveled 100 light years. That's a tiny part of the galaxy. Most stars haven't heard from us yet, so the best strategy might be to listen first, to keep watching the stars where life could be, until something speaks. The Puzzle of Star System, HD 164595. HD 164595 is a star system that sits about 94 light-years away in the constellation Hercules. The star is slightly older and a bit cooler than our Sun, and it's been known to astronomers for years. But in 2016, this quiet star system suddenly found itself in the center of a growing conversation about possible signs of intelligent life beyond Earth. The event that sparked it all was the detection of a strong radio signal, recorded by Russian scientists using the Ratan 600 radio telescope. Years later, with more attention and data available, researchers revisited the incident in 2019, trying to make better sense of what had actually been picked up. The original detection, buried in observational data, wasn't made public right away. It came from a single observation made in May 2015, but wasn't formally discussed until 2016, when it was highlighted at a meeting of the International Academy of Astronautics. That's when the scientific community and the general public began to take notice. The signal was narrowband, centered around 11 GHz and strong enough to stand out from the usual noise. It lasted for only a few seconds. The signal was associated with the direction of HD 164595, a known star system that hosts at least one Neptune-sized exoplanet. That made it a puzzle worth investigating. By 2019, researchers had returned to the original data, hoping that newer tools and better context might help explain what had been found. Interest from the Breakthrough Listen project and other SETI teams led to a closer re-examination of the signal's characteristics. The signal hadn't repeated, and that made things more complicated. If a signal can't be traced again, it becomes much harder to rule out simple equipment issues, interference, or even noise from deep within the telescope itself. The signal's characteristics were studied closely. It had the narrowband profile and was focused in a frequency range that doesn't occur often in nature. There was no known Earth-based satellite or transmission scheduled in that exact band at that time, at least not officially. And the strength of the signal suggested something powerful, if it had really come from the HD 164595 system. That "if" became the center of the debate. The Ratan 600 telescope is not like more modern radio arrays. Its beam shape is wide, and it lacks some of the resolution that newer telescopes offer. That means its ability to precisely locate where a signal is coming from isn't perfect. It was possible, scientists admitted, that the signal might have come from somewhere else in the sky, or even from Earth. The technology used in the detection could not rule that out. In the 2019 analysis, scientists also rechecked satellite databases and global radio frequency charts. While no matching Earth-based source could be confirmed, there was still a chance that military or classified transmissions could have caused the event. These aren't always publicly listed. Satellites that operate in similar frequency bands might have passed through the region at the time, sending bursts of data that could mimic a space-based signal. This has happened before. In some cases, even distant radar systems or local electronics near observatories have created strange, short-lived blips. Still, The signal was interesting enough that other observatories were brought in to take a second look. They didn't detect anything unusual in follow-up observations. That lowered the odds that the signal was part of an ongoing transmission or a repeating event. If it had been a steady communication attempt from an alien civilization, scientists reasoned, they would have expected to see some kind of pattern or recurrence. The signal triggered questions about the known planet in the HD 164595 system. The Neptune-sized world, while intriguing, doesn't sit squarely in the habitable zone. That means it's unlikely to support Earth-like life on its surface. But that doesn't rule out everything. If the planet had large moons, or if there were other undiscovered planets in the system, there could still be environments where life might exist. Some scientists speculated about the possibility of advanced civilizations using satellites or orbiting platforms to transmit signals, making the exact origin of a broadcast harder to trace. It was, they admitted, mostly guesswork. But part of SETI's role is to explore those guesses, test them, and rule them in or out with data. The work hasn't stopped. Scientists are still scanning HD 164595 when time allows, looking for any repeat signals. The area of the sky is now part of the regular survey list for several SETI observatories. While nothing new has been found from that system so far, it remains on the radar, both literally and figuratively. Unresolved signals from Gliese, 581G, a controversial case in alien signal research. Gliese 581G, a planet orbiting a red dwarf star just over 20 light-years away, became one of the most talked-about places in the search for life beyond Earth. Discovered in 2010, the planet's location, its size, and its temperature made it a strong candidate for life. But what really made Gliese 581G famous wasn't just its potential habitability. It was a handful of strange, unresolved signals detected from its direction, which led to a wave of excitement, skepticism, and debate within the scientific community. A team of astronomers using the Keck Observatory in Hawaii were studying tiny shifts in the light from the star Gliese 581, looking for the gravitational tug of orbiting planets. In their data, they claimed to have found a signal that pointed to a planet in just the right orbit for life. Within days of the announcement, SETI researchers turned their instruments toward the star. The initial signal of interest wasn't a loud or clear one. It was subtle, barely above the noise. A faint radio signal, narrow in frequency, that seemed to come from the general direction of Gliese 581G. The SETI Institute pointed the Allen telescope array toward the system, scanning across different radio bands and watching for anything that looked unnatural. For a short time, they found something, a recurring spike that raised eyebrows. It didn't match known satellite paths. It didn't follow the usual patterns of background cosmic radiation, and it didn't repeat in a way that could be easily explained by natural causes. But the signal didn't last. It faded, then returned, then vanished again. Scientists ran checks. Could it be Earth-based interference? Could it be caused by the instruments themselves? The problem with faint signals is that they can fool even experienced observers. Something as simple as a malfunctioning radio component or a bounce of radio waves from a passing satellite can show up as a blip in the data. As weeks passed, the debate around the signal and the planet itself grew more intense. A second group of astronomers challenged the existence of Gliese 581G entirely. They said the data used to find the planet wasn't strong enough. They argued that the signals detected by Keck could have been noise, not proof of a new world. If the planet didn't exist, then any radio signal coming from that part of the sky couldn't be coming from it. That alone cast a long shadow over the idea of extraterrestrial life in the system. Other telescopes were directed at the star. Observations continued over the next few years. Teams in Europe and North America ran separate studies. Some found hints that supported the planet's existence, while others said the data didn't hold up. Meanwhile, the strange radio signals remained unresolved. No one could say for sure what they were or where they came from. They were just strong enough to be noticed, just weak enough to be doubted. Red dwarf stars like Gliese 581 are known for their long lives and violent tempers. They often emit strong flares. These flares can also strip away the atmospheres of nearby planets, making life difficult. But they can also create strange signals, especially if they're interacting with planetary magnetic fields or surrounding gas. Some scientists argued that what SETI researchers picked up might not have come from an intelligent source at all. It could have been a side effect of natural star activity. Still, there were parts of the signal that didn't match what would normally be expected from flares. The narrowband nature of it was unusual. That's why SETI scientists were careful not to dismiss the possibility too quickly. Even though the signal was weak, it had characteristics that merited more attention. The situation with Gliese 581G highlighted how difficult it is to confirm a true extraterrestrial signal. First, you need to confirm the planet is real. Then you need to detect a signal that is not only unexplained, but also repeated and verifiable by other observers. And even then, you need to rule out every possible Earth-based cause. That's a high bar, and the Gliese 581G case didn't clear it. But it didn't fail completely either. It simply sat in a grey area, interesting enough to study, but not strong enough to claim discovery. Over the years, interest in Gliese 581G has faded somewhat. The focus has shifted to other exoplanet systems like TRAPPIST-1 and Proxima Centauri. In 2014, another twist appeared. A study claimed that earlier reports of Gliese 581G and other planets in the system might have confused stellar activity with planetary signals. Instead of planets tugging on the star, it could have been magnetic storms and other internal processes making the star's light wobble. If true, that would mean the planet and the excitement around it might have been based on a mistake. But even then, not everyone agreed. Some astronomers insisted that at least some of the planets, including Gliese 581G, were real. That's how science works, by argument, repetition, and caution. The Gliese 581G case shows that progress in the search for life doesn't come in big leaps. It comes in small steps, backed by evidence that is often fragile. When a signal comes in, it has to survive the toughest scrutiny. Most don't. But the few that remain unexplained keep the questions alive. Exploring the perplexing signals from the Cygnus constellation. Cygnus contains a number of pulsars, and their rhythmic pulses have helped scientists understand more about extreme physics. But among the normal activity were a few signals that didn't quite fit. They didn't pulse regularly. They weren't broadband like natural bursts from gas clouds or star flares. And most importantly, some were very narrowband. One of the best-known stars in this region is KIC 8462852, also known as Tabby's star. But it's not just Tabby's star that's of interest. The entire Cygnus region is rich in targets, from stars with planets to dense star clusters. In fact, this is the area where the Kepler Space Telescope stared for years, capturing data on hundreds of stars. In the radio world, several surveys have aimed telescopes at Cygnus. The Green Bank Telescope, the Allen Telescope Array, and others have scanned the region again and again. Among the interesting findings was a narrowband signal detected in the early 2000s during a sweep of the Kepler field. For a short moment, it looked like a possible hit. Scientists catalogued it, ran follow-up observations, and then added it to the long list of perplexing events. Signals that seem artificial in form, but vanish before they can be studied properly. The problem with these kinds of signals is their brief appearance. But Cygnus has had more than one of these. Over time, small, unexplained signals have continued to show up in its direction. Each time, they're checked against known causes. Each time, there's no definitive explanation. They stay on the edge of scientific certainty. SETI researchers have a name for this zone of uncertainty. They call it RFI limited, meaning the ability to detect true alien signals is limited by radio frequency interference. When scientists aim a radio telescope at the sky, they have to filter through this noise. Some signals pass through those filters and are flagged as interesting. The ones from Cygnus keep doing that, and that keeps scientists coming back. One of the more debated cases came from a project known as META, or Megachannel Extraterrestrial Assay, which ran during the 1980s and 1990s. It was designed to detect narrowband radio signals, scanning large parts of the sky with high-frequency resolution. In the data, researchers found several signals near Cygnus that looked promising. Some had the right drift rate, the right signal width, and came from star fields with potentially interesting targets. But none of them ever repeated. Scientists catalogued them, gave them ID numbers, and moved on, hoping future technology might help confirm what they were. That's one of the frustrating truths in SETI. Most of the signals that raise eyebrows don't repeat, but without repetition, you can't ask follow-up questions. That's what happened with the famous WOW signal, and it's the same challenge that faces the Cygnus signals. Despite the setbacks, researchers have continued to update their methods, and Cygnus remains on the list of priority targets. One reason for this is the number of stars in the region. Cygnus is part of the Milky Way's disk, where stars are packed more densely than in other parts of the sky. That means more chances to find planets, and more chances that one of those planets has developed technology. Kepler confirmed this by discovering hundreds of exoplanets in Cygnus. Many are Earth-sized, some are in the habitable zone, and a few show signs, though very faint, of potential atmospheres or unusual light behavior. That makes them perfect targets for deeper study, including the search for techno-signatures. Techno-signatures are what SETI is really hunting. A planet with trees or oceans doesn't broadcast anything, but a planet with cities, satellites, or radio towers might. A techno-signature could be anything from a powerful directed radio beam to a broad signal leaking into space. It might even be a shadow that dims a star in a strange way. Cygnus is full of candidates for this kind of study, which is why it continues to draw attention. Some hope that one day a signal from Cygnus will break the pattern. It won't be a single blip, but a steady, repeating message. One that can be confirmed by multiple telescopes. One that matches no known natural source. Until that happens, the signals from Cygnus will stay in that strange, unsatisfying space between doubt and discovery. Pulsars, magnetars, and quasars are cosmic beacons sending us a message. If the neutron star's magnetic field and rotation line up just right, it sends beams of radio waves out into space, sweeping around like the beam of a lighthouse. Every time the beam points toward Earth, we see a pulse, hence the name pulsars. These pulses are so regular that some pulsars are more accurate than atomic clocks. That precision fascinated scientists from the start. If nature could create something so steady and reliable, could an advanced civilization do the same thing, on purpose? Could they use something like a pulsar to encode or transmit a message across vast distances? Over the years, SETI researchers and astronomers alike have wondered whether certain pulsars might be altered or used in some way. The reasoning is simple. If you wanted to send a signal that could last millions or billions of years and remain detectable through the noise of the universe, a pulsar would be a good choice. It's stable, it's bright, and its natural rhythm could be changed, just slightly, to carry a message. Even small irregularities in a pulsar's beat might carry information. That's speculative, of course, but some still scan pulsar data for any signs of odd behavior. Unlike the steady rhythm of a pulsar, a magnetar's signals tend to be messy and unpredictable. But in rare cases, they do repeat. And because their signals are so powerful, they can travel long distances, exactly the kind of behavior that SETI researchers find interesting. Could a magnetar be modified or used as a power source to create a deliberate beacon? Could the sudden burst from a magnetar be focused or directed, perhaps using some form of alien engineering? Some think that's far-fetched. Others argue that if a civilization had access to that kind of energy, it would make sense to use it as a way to get noticed. It wouldn't need to be a message with words or language. just a sign that something intelligent was out there. A bright burst, repeating in a way that nature couldn't easily explain. That idea drives part of the ongoing search for unusual patterns in the behavior of neutron stars. Any anomaly, any deviation from what physics predicts gets a second look. Quasars, on the other hand, are not neutron stars. They are something far more powerful. Quasars sit at the hearts of galaxies. They are powered by supermassive black holes surrounded by disks of hot glowing gas that heats up and emits intense radiation, sometimes across the entire electromagnetic spectrum. Quasars are among the brightest objects in the universe. They can be seen from billions of light years away. The light and radio waves from quasars aren't regular in the way pulsars are, but they are loud. What if a highly advanced civilization could harness or manipulate the energy near a black hole? That kind of power is hard to imagine. But if they could, it would give them a way to broadcast across the entire universe. No one has found clear evidence that a quasar has been used this way, but the idea has appeared in both science fiction and serious scientific papers. The raw energy is there. The scale is there. And if anyone wanted to get noticed by civilizations in faraway galaxies, few tools would be more effective than a quasar. These thoughts about pulsars, magnetars, and quasars don't necessarily mean that aliens are using them, but they serve as a reminder that natural objects in the universe can sometimes mimic the very things we'd expect from intelligent life. They flash, they pulse, they burst. And in doing so, they challenge scientists to think more carefully about what a signal really looks like. It also shows how SETI has changed over the years. In the beginning, the search focused mostly on pure tones at specific frequencies. Those signals are still important, but now researchers also look at a wider range of possibilities. That includes natural objects behaving in unusual ways. Everything is on the table, as long as it stands out from the background, and the background is noisy. Radio telescopes pick up signals from Earth, from satellites, from nearby stars, and from distant galaxies. Sorting through all that data requires new ways of thinking. Even now, decades after the first pulsars were discovered, new ones are still being found. So are new magnetars, and quasars continue to fill the sky with light and radiation, coming from the oldest and farthest corners of the universe. Each one adds to our understanding of what the cosmos can do on its own, and what might happen if something else, something intelligent, gets involved. The role of multidimensional space in potential signal transmission. The idea that space might include more than the three dimensions we know, length, width, and height, is not new. For decades, scientists have wondered if the universe could be made up of more dimensions than we can perceive. These extra dimensions wouldn't be visible or easily experienced, but they might still affect how things move or interact in our universe. Could highly advanced aliens use these hidden dimensions to send signals or communicate? It's a hard thing to picture. We live in a world where everything has height, width, and depth. Time gives us a fourth direction, though it's not something we move through freely. Theories like string theory, which try to explain how gravity and particles fit together, suggest there might be as many as 10 or 11 dimensions. Most of these would be curled up so small that we can't detect them. But in theory, a species far ahead of us in science might have found ways to interact with them. And if that's true, they might also have found ways to send messages through them. Imagine a world that exists alongside ours, sharing the same space but in a direction we can't see. If an alien civilization knew how to manipulate this hidden space, they might be able to send a signal that appears suddenly, without traveling across the visible sky. To us, it would seem like the signal just came out of nowhere. No path, no delay, just a sudden burst of information. That could explain some of the strange signals we've seen that don't repeat or follow a clear direction. There's also the idea that using higher dimensions might let a signal bypass ordinary space. In three-dimensional space, sending a message to another star takes years or even centuries. A radio wave travels at the speed of light, But even that isn't fast enough for a back-and-forth conversation with someone 100 light-years away. If a signal could take a shortcut through a higher dimension, it might arrive much faster, possibly even instantly. That would change everything about how we search for life in the universe. These ideas are still theoretical, but there's some math to support them. In certain models of the universe, gravity might be able to leak into higher dimensions. If that's true, then energy or information could possibly follow. Some experiments at places like CERN are trying to test this by smashing particles together and looking for signs of energy disappearing into another dimension. So far, nothing has been found, but the possibility remains. Even without solid proof, some researchers think it's worth including higher dimensional ideas in the search for alien signals. Most of SETI's work has historically focused on radio waves, and more recently, optical lasers. But if a signal came from a different kind of space, it might not show up as a wave at all. It might look like a sudden change in gravity, or a strange burst of heat with no source. It might even take the form of data embedded in quantum particles or some kind of temporary change in the structure of space itself. This opens up a new problem. If a signal uses higher dimensions, how would we even recognize it? What if the signal isn't in the usual form of a wave or a pulse? What if it's something like a brief warp in local space? Something that instruments wouldn't even classify as a message? That's a big part of the challenge. We may already have detected strange things that don't match our expectations, but dismissed them because they didn't fit the known categories. There are also philosophical questions that come with this idea. If another species has access to higher dimensions, it might also think in ways we can't understand. To them, communication might not be about sending and receiving at all. It might be about aligning with certain patterns in reality, or tuning into layers of the universe we don't know exist. Their version of a message might be something we'd never interpret as communication. It might be a shift in background radiation, or a faint flicker in the fabric of space. There have been a few real-world observations that push the boundaries of what we know. Some cosmic rays arrive with far more energy than they should. Some particles seem to appear without a clear source, and some fast radio bursts don't match any known natural process. None of these have been tied to higher dimensions, but if we don't look for something, we probably won't find it. Some have tried to build models that test how a higher dimensional signal might behave. They've asked, if an alien civilization used a higher dimension to send a gravity-based signal, how would that affect the movement of stars or gas in a nearby galaxy? Could we pick up a signature that says something passed through, even if we don't know what it was? Others have asked whether quantum entanglement could be used to transmit data in a way that skips over space entirely. Though the rules of quantum physics say entanglement can't carry messages faster than light, some theorists think that might only be true in our visible dimensions. In science, most good ideas start as guesses. They often sound wild at first, but over time, as tools improve and understanding grows, some of these guesses become part of accepted knowledge. The idea of higher dimensions is still far from being proven, but it's taken more seriously than it was a generation ago. It has already helped shape theories about gravity, black holes, and the birth of the universe. Now, it's starting to influence how we think about the search for extraterrestrial life. This doesn't mean we should stop looking for ordinary radio waves or laser pulses. Those are still the best bets. They're the kinds of signals we would send ourselves. But the possibility of other forms of communication, ones based on deeper structures of space, means that we shouldn't limit our search to just what we know. If there are civilizations out there that have been around for millions of years, they might not be using radio at all. They might be using the universe itself as their message board. Are we listening in the wrong frequency? The radio spectrum is wide. It stretches from very low frequencies used for long-range communication on Earth to higher frequencies near the microwave band. Early SETI projects mainly searched around 1 to 10 gigahertz, a region often called the waterhole. This nickname comes from the fact that it's flanked by the natural emission frequencies of hydrogen and hydroxyl, the components of water. Scientists thought that any life interested in reaching out might see this quiet part of the spectrum as a natural meeting place, but there's no guarantee that alien life would think the same way. Some experts have started looking beyond the traditional radio window. They point out that there are many other parts of the electromagnetic spectrum that might be better suited to sending or receiving signals, depending on how advanced a civilization is. For example, higher frequency millimeter waves or even terahertz signals could carry more data in a shorter time. These signals are harder for us to use now because they require more precise equipment, but for a civilization 1,000 years ahead, they might be routine. There's also the possibility of signals coming in parts of the spectrum that we barely monitor. The far-infrared, ultraviolet or X-ray bands don't get much attention in most SETI projects. Instruments that detect these wavelengths are more expensive and often serve other goals, like studying galaxies or black holes. But if a message were hidden in a beam of X-rays or encoded in a burst of gamma rays, we might not even recognize it as artificial. It would be logged, stored, and likely passed off as some unknown natural event. This raises the issue of assumptions. Every search for alien life includes choices about where and how to look. Most of those choices are based on what we know about ourselves and our own technology. But what if we've missed something? What if advanced civilizations discovered, long ago, that certain frequencies are better for long-distance communication, ones that we simply haven't thought to explore? One example of this is the idea of using neutrinos. These are tiny particles that barely interact with matter. They can pass through stars, planets, and even entire galaxies without being blocked. That makes them a possible tool for communication across very long distances. But detecting neutrinos is extremely difficult. It takes massive underground detectors filled with special materials. And even then, only a few can be spotted. If a signal was sent using neutrinos, we might already be swimming in it without knowing. Another possible type of signal could be based on gravitational waves. These ripples in space-time were first detected in 2015, proving a key part of Einstein's theory of relativity. Since then, scientists have watched as black holes and neutron stars collide, sending out waves that stretch and squeeze the fabric of space. Could a highly advanced civilization use those waves to carry information? It's not something we know how to do, but if someone out there has found a way, our current instruments might not be sensitive enough to pick it up. There's also the matter of artificial signals hidden in natural-looking bursts. It's possible that messages could be embedded inside normal astronomical phenomena. We might have already received these signals, but misinterpreted them as random noise or unexplained natural events. The way we process data also matters. What if an alien signal isn't narrow at all? What if it's wideband or shifts its frequency over time? What if it doesn't stay in one place in the spectrum or comes in short, scattered bursts that don't repeat? Many traditional SETI searches would miss such a signal completely. There's interest in reanalyzing old data with new methods to search for these possibilities. SETI has decades of recordings stored away, some of them from early projects like Project Phoenix or the SETI at Home effort. With better software and faster computers, we might be able to go back and find something that was missed the first time. Maybe a weak or drifting signal, hidden between stronger ones, or a pulse that was too fast or too faint to register with earlier equipment. Beyond technical issues, there's a cultural side to this too. For many years, the search for extraterrestrial life focused on what seemed logical and affordable at the time. That meant using Earth-based radio telescopes and listening to familiar frequencies. But now, with better technology and more cooperation across countries, the field is opening up. New observatories and upcoming missions like the Origin Space Telescope might allow researchers to check parts of the spectrum they've never explored before. There's no way to know what we might find. It could be nothing, or it could be the key to everything. Even something as simple as a shift in thinking could change the outcome. If we stopped biasing our assumptions and started looking for patterns in all kinds of light, waves, and particles, we might begin to notice things that were always there. The role of quantum entanglement in alien communication. Quantum entanglement has puzzled scientists since the earliest days of quantum physics. It is a strange and fascinating idea. Two particles can become linked in such a way that apart they are in space. A change to one seems to instantly affect the other. It seems to break the rules of how things are supposed to work. Normally, nothing can travel faster than light. Yet entangled particles seem to share information instantly, no matter how far apart they are. Could alien civilizations be using quantum entanglement to communicate across space? Signals based on light take time to travel. If someone is trying to talk to us from across the galaxy, the delay would be thousands, even millions of years. In that case, a back-and-forth conversation would be nearly impossible. But if alien beings have figured out how to use quantum entanglement, they could, in theory, send messages instantly, no matter the distance. When two particles are entangled, they share a kind of invisible link. You can separate them by any distance, across a lab bench or across a galaxy. And when you measure one particle, the result seems to instantly decide the state of the other. It's as if they're part of a system that exists outside of regular space. But here's the strange part. According to most scientists, entanglement doesn't allow you to send clear messages. You can't control what result you get when you measure a particle, so you can't use it to transmit chosen information, at least not in any simple way. Still, this limitation hasn't stopped researchers from exploring the idea further. Some believe that there might be advanced methods of using entangled systems together with classical signals to get around this problem. Others think that we might simply not understand the full picture yet. It's possible that alien civilizations have discovered ways of using quantum mechanics that we haven't even imagined. After all, quantum physics is still young. Our knowledge of it is only about 100 years old. A civilization 1,000,000 years older than ours might know tricks of physics that seem impossible to us. If an alien species had found a way to use entanglement for communication, it would change everything. Messages could be sent instantly across galaxies. The delay of light-speed communication would no longer matter. Civilizations could stay in close contact with one another no matter how far apart their planets were. This kind of technology might allow entire networks of advanced beings to remain connected in ways we can't yet understand. It could also explain why we haven't detected any obvious signals. Our antennas and telescopes would be blind to it. Quantum systems can be incredibly delicate. They can fall apart or decohere when exposed to outside forces. This makes them hard to detect. A message sent through entanglement might leave behind no signal, no trail, nothing we can measure in the usual way. Yet some scientists are working on ways to test whether quantum systems can be used for communication. In recent years, researchers have made progress in building quantum computers, quantum sensors, and even quantum networks. Some experiments have shown that entangled particles can be used to detect changes in a system or to share secret keys for encryption. These are early steps, but they show that quantum mechanics may have practical uses we are only starting to discover. If humans are just beginning to understand these ideas, then it's reasonable to wonder what an older, more advanced civilization might have achieved. They may have built devices to talk across vast distances without any delay. They might even have built a kind of quantum web, a network of entangled systems spread across the galaxy, silently passing messages from one world to another. If such a network exists, it would be invisible to us until we figured out how to access it. If quantum communication is possible, would aliens want us to discover it? Maybe they're waiting for us to unlock the next level of physics before joining their network. There's also a risk that comes with this kind of communication. Because entanglement is so delicate, messages could be fragile. A single mistake could ruin the signal. That might be another reason we haven't detected anything. Maybe the messages are coming in, but we don't know how to preserve or decode them. Or perhaps the senders use a form of encoding that makes the message look like background noise to us. Interest in quantum communication is growing. Some scientists are developing space-based experiments to test how entangled particles behave in orbit. Others are designing detectors that might be able to sense strange correlations between far-off events. These efforts are small, but they reflect a growing belief that the future of communication may lie in the strange world of quantum mechanics. If aliens are out there, and if they are using quantum entanglement, we may need to follow the same path in order to find them. The mysteries of gravitational waves. Could they carry messages from beyond? Since their discovery, gravitational waves have become a growing part of astronomy. They allow us to detect events that don't emit light or radio waves, things like black hole mergers, neutron star crashes, and possibly other strange cosmic activities. But could these waves carry more than just signs of collisions? Could they carry messages, information sent across the galaxy, not through light or radio, but through the very fabric of space itself? At first glance, the idea seems far-fetched. Gravitational waves are caused by incredibly massive objects moving at high speeds. They're not easy to produce. In fact, the only natural sources we know of that make them are extreme: black holes, neutron stars, and other dense, energetic things. But that might be the point. If a civilization wanted to send a message across the universe in a way that could not be blocked, weakened, or confused with noise, gravitational waves might be the most secure method available. One reason scientists are curious is because gravitational waves are almost impossible to stop. They pass through matter without being absorbed or scattered, unlike radio or light waves, which can bounce off dust or be absorbed by gas clouds. That means a signal sent as a gravitational wave could travel across entire galaxies without losing much of its power. It could reach us just as strong and clear as when it was first created, if we had the right tools to understand it. The problem is, right now, we don't. Our gravitational wave detectors are still in their early stages. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, and its European partner Virgo are incredibly sensitive, but they can only detect strong signals from giant events. They look for short bursts, ripples that pass through Earth for just a second or two, created by things like black hole mergers. If a signal were encoded in a gravitational wave, we'd need to be able to recognize a pattern in that brief event. And so far, all the waves we've found match what we expect from natural sources. Still, some researchers are starting to explore how information could be hidden in these waves. One idea is that a civilization might use something like a binary system orbiting each other in a controlled way. If they could adjust the distance or speed of these objects, they might change the shape of the gravitational waves they produce. That shape could carry a message, like how sound waves can carry music or speech. Another idea is that instead of using natural objects, an advanced civilization could build something completely artificial, a machine designed to produce gravitational waves. This would be incredibly difficult, requiring control over masses far beyond anything we've ever handled. But it's not completely impossible in theory. Some have speculated about gravitational wave beacons or stellar lighthouses built to send messages across the stars. If such a thing existed, it might produce waves in a regular repeating pattern. Even if the messages themselves were not sent intentionally, there's still value in paying attention to gravitational waves more closely. They give us a view of places we can't see any other way, like the inside of a black hole collision. If intelligent life exists around those regions, they might also be affected by, or even take advantage of, the same physics. In other words, learning more about gravitational waves might help us understand environments where life could exist, or where civilizations could evolve to use those waves for their own purposes. There's also a growing interest in combining data from gravitational waves with data from light, radio, and other forms of energy. This is called multi-messenger astronomy. By comparing different types of signals from the same event, scientists can get a more complete picture of what's happening. If we only look in one area, say radio waves, we might miss the bigger message. But if we start to detect patterns that match across gravitational waves and neutrinos, for example, that could be a clue. Of course, there are many technical challenges. Detecting gravitational waves is already hard. Interpreting them is even harder. The waves themselves are incredibly subtle, stretching and squeezing space by less than the width of a proton. Our detectors have to be kept perfectly still and free from all vibrations, including traffic, wind, and even earthquakes. And the signals they find have to be separated from all the other movements on Earth and in the equipment itself. Adding a search for encoded messages into that process is like trying to find a whisper in the middle of a rock concert. But new observatories are being built that will be even more sensitive than LIGO. One of them is called LISA, the Laser Interferometer Space Antenna. Unlike LIGO, which is on Earth, LISA will float in space, far from the noise of our planet. It will consist of 3 spacecraft flying in a giant triangle, using lasers to measure tiny changes in distance between them. LISA will be able to detect lower frequency gravitational waves, the kind that might come from slower moving or more stable sources. Some scientists think this could include waves from artificial or unusual systems. Other future projects aim to use natural detectors, things like pulsars. If a gravitational wave passes between us and a pulsar, it should slightly change the timing of its beams. By studying many pulsars across the sky, scientists can build a kind of giant gravitational wave detector. This method is already being tested by the Nanograv project. For now, the mystery of gravitational waves continues. But somewhere out there, hidden in the ripples of space and time, there could be a message waiting, carried not by light or sound, but by the very shape of the universe itself. The Fermi Paradox, the great silence of the universe and its implications. There are billions of stars in the Milky Way galaxy. Many of those stars have planets. Some of those planets are similar to Earth. Life could start on some of them. If even a small number of those planets developed intelligent life, and if even a smaller number developed technology, then those civilizations could spread out. They could explore, they could send signals, they could build machines to cross the stars. But so far, we've found no solid proof that anyone is out there. This silence is what Enrico Fermi asked about in the 1950s. He was a physicist known for his work on nuclear energy. During a casual conversation with colleagues about aliens, he asked, "Where is everybody?" That simple question became the heart of the paradox. The numbers say aliens should be out there. The sky says otherwise. Over time, scientists and thinkers have come up with many possible answers to the Fermi paradox. Some believe we're just early. Maybe Earth is among the first planets to form intelligent life. In that case, we wouldn't expect to see signs of others yet. If life takes time to evolve, maybe we are the signal, the first voice in a silent sky. Others think we may be too late. Perhaps civilizations do form on other planets, but they don't last long. They destroy themselves through war or environmental collapse before they can explore space. They might build powerful machines or artificial intelligence that turn on them. If that happens often, then life might appear many times, but die out just as quickly. There's also the idea that civilizations stay quiet on purpose. This is called the zoo hypothesis. It suggests that alien life knows we're here but chooses not to contact us. Maybe they're watching us from a distance, waiting for us to grow. Maybe they follow some rule about not interfering with younger civilizations. If that's true, we might never hear from them until we pass some unknown test. Another possibility is that alien signals are all around us, but we can't recognize them. Their technology might be so advanced that their signals are undetectable for us. Or maybe they communicate in ways we don't understand, through gravity, quantum particles, or things we haven't discovered yet. It's hard to find something when you don't know what it looks like. Some scientists suggest that space is just too big. Even if a civilization is sending signals, they might not be reaching us. A signal could take thousands of years to arrive. It might pass by Earth while we weren't listening, or it could fade before it gets here, becoming too weak to notice. Civilizations might also only send signals for a short time. If they stop transmitting before we start listening, we'd miss them completely. There's also the idea that we haven't looked hard enough. Most of our SETI searches have covered only a small part of the sky for a short period of time, using a narrow range of frequencies. It's possible that as our technology improves, we'll discover something that was there all along. Still, many researchers find the silence troubling. They call it the Great Silence, the idea that space should be filled with signals. But it's not. This silence forces scientists to ask bigger questions. Are we alone? If we are, what does that mean? If intelligent life is rare, does that make us special? Or does it mean that something always goes wrong, something we haven't faced yet? One idea, known as the Great Filter, suggests that there's a hard step in the path from simple life to intelligent spacefaring beings. That step could be behind us, or ahead of us. If it's behind us, that means life is hard to start. Maybe Earth is incredibly lucky. Maybe it's rare for molecules to form into living cells, or for single cells to become complex life. In that case, we may be among the very few planets where this happened. But if the filter is ahead of us, then we might be in trouble. It could be that civilizations always reach a point where they make a mistake they can't undo. They might build weapons that destroy their planet. They might rely on systems that collapse. If this is the case, the silence of space is a warning. It's the sound of others who came before us and didn't survive. The Fermi paradox has also changed how some scientists think about alien life. Instead of asking, "Where are the aliens?" they now ask, "What does it take to become a long-lived civilization?" This shift focuses attention on our own future. If we want to last long enough to hear from others, or to visit the stars ourselves, we may need to learn from the silence. Some thinkers believe we should keep searching no matter what. They argue that even one signal would change everything. It would open the door to a new understanding of life, science, and the universe. That possibility is enough to keep many scientists looking, listening, and hoping. Others think we should be careful. They warn that sending messages into space could be risky. We don't know who might hear us. In the wrong hands, our signals could bring danger instead of answers. Some call this the dark forest idea, where everyone hides in fear, not wanting to be found. Whatever the truth may be, the Fermi paradox remains one of the biggest unsolved questions in science. It pushes us to ask more, to search harder, and to question our place in the cosmos. The silence may feel lonely, but it also invites curiosity. The silent watchers. What if aliens are already watching us? The zoo hypothesis, or cosmic quarantine, suggests that advanced civilizations may know about Earth and the human race, but are choosing to stay quiet and not interfere. From their point of view, Earth might be like a natural reserve, a place where intelligent life is still in its early stages, just beginning to understand the universe around it. To interfere with that development, whether through contact, influence, or technology, might be seen as unethical or dangerous, so they stay hidden, watching silently from afar. It's not such a strange idea when compared to how we treat life on Earth. Biologists observing wild animals will often hide or use remote cameras so that their presence doesn't change the animal's behavior. Some countries have protected areas where human contact is limited to preserve the environment and allow species to grow without interference. If an alien species has been around for millions of years, they may see us in a similar way, as something fragile, not yet ready to be part of a larger galactic community. For this theory to work, aliens would need to be very advanced, not just technologically but socially. They would need a set of rules or shared agreements about how to treat developing civilizations. That assumes a level of unity or cooperation that humanity itself hasn't fully achieved. But maybe this is the key to survival in the universe. Civilizations that learn how to cooperate, how to avoid war, how to grow slowly and carefully, are the ones that last long enough to explore the stars. And maybe part of that growth includes learning when not to act. Some people take the idea further, suggesting that aliens might have visited Earth in the distant past, leaving behind no trace or only subtle signs that we haven't recognized yet. Others imagine that alien probes, small, quiet, and hard to detect, might be orbiting Earth right now or hiding on the Moon, silently gathering information and reporting back. If their technology is far beyond ours, detecting them would be incredibly difficult. They could be listening to our radio and television broadcasts, watching our scientific growth, waiting for the moment when we become ready for contact. But what does ready mean? That's a harder question. It might mean achieving a certain level of technology, like the ability to travel between planets or control powerful energy sources without destroying ourselves. It might also mean reaching a kind of moral or social maturity, overcoming violence, inequality, or short-term thinking. Aliens might be waiting for us to pass some invisible test. Until then, they observe and say nothing. If aliens are already watching us, would there be any way to know? Some scientists argue that we might never be able to tell. If their goal is to remain hidden, then any signs of their presence would be masked. Any signal they send might be encoded in ways we can't understand. Any probe they've placed could be built to mimic natural objects or designed to avoid detection altogether. Still, others think that subtle clues might exist. A few SETI researchers have looked at odd patterns or energy signatures that don't quite fit, and wondered if these might be signs of alien monitoring stations, cloaked satellites, or devices set up to track young civilizations like ours. But so far, nothing has been proven. The clues are faint, and science demands evidence. There's also the possibility that we are simply not interesting enough yet. To a civilization that's millions of years ahead of us, humanity might seem primitive. Our struggles, our conflicts, even our science might look like the early steps of a long journey. We might not stand out. We might be just one of many species they're watching, each one at its own pace of development. The quiet may also be a way to avoid risk. If multiple civilizations are watching others from a distance, and none of them know who can be trusted, it might create a culture of caution. Speaking first could reveal your location, your technology, and your weaknesses, so no one speaks. Everyone watches. In that kind of universe, being silent is about survival. In this scenario, Earth becomes part of a quiet galaxy filled with watchers, each one waiting for signs that others are peaceful, advanced, and ready. If this is true, then it could be a long time before we hear anything. Or it could mean that we've already been heard, and now they're just watching to see what we do next. Some believe that this idea brings comfort, the thought that we're not alone, that someone is out there who knows we exist. It suggests a galaxy that isn't hostile, just patient. Others find it unsettling. They imagine eyes in the dark following our every move with goals and motives we can't understand. But whatever feeling it brings, the theory has a strange kind of logic. It explains the silence not as a lack of life, but as a decision, a choice to wait. Maybe we are part of a silent experiment. Maybe we are surrounded by watchers who have seen many worlds rise and fall. And maybe someday, when we've grown a little more, one of them will break the silence. Or maybe they'll wait a little longer. How close are we to decoding complex alien communications? When scientists talk about the search for alien signals, one of the biggest questions they face isn't just about finding the signals, it's about understanding them. Even if a message came from space tomorrow, and it was clearly artificial, that would only be the beginning. The real challenge would be figuring out what it meant. Our current technology has come a long way in detecting strange signals, but decoding something complex, especially if it was created by a species far more advanced or different from us, is still a huge hurdle. One reason for this difficulty is that we don't have a shared language or a shared reference point with any possible alien civilization. Everything we know, our symbols, our ideas, our math, even our understanding of time, has developed on Earth. A signal from another world might use a completely different logic or structure. It might not even use sound or language in the way we do. If the message came in the form of raw data or a mathematical code, we'd have to guess at its structure before we could even begin trying to read it. And some researchers believe that mathematics could be a kind of universal key. Numbers and patterns are not limited to Earth. They exist everywhere. So if an alien civilization wanted to send a message that others could understand, they might use mathematical sequences like prime numbers, the Fibonacci series, or geometric shapes as a starting point. These kinds of signals would stand out in the noise of space because they're unlikely to occur naturally, but even then, that would only be the opening handshake. A real conversation would be far more complicated. To understand any message beyond a simple signal, we would need to decode its symbols, structure, and meaning. This process is called decryption, and it's something we already use here on Earth for computer security, secret communications, and even deciphering ancient texts. But in those cases, we usually have at least some context. We know the language group, or we have similar examples to compare. With an alien signal, we might not even know if we're looking at words, pictures, sounds, or something else entirely. The tools we have today for this kind of work include machine learning, pattern recognition software, and large computing networks. These systems can scan through millions of possibilities, looking for patterns or repetitions that might mean something. Researchers are training these programs using data sets that include known human languages and even fictional ones to try to make them better at spotting structured communication. Still, this is early work. If an alien signal used an unfamiliar logic, our current systems might miss it entirely. Another issue is bandwidth and storage. Some of the signals from space, especially ones like fast radio bursts, are extremely short. They last only milliseconds, but they can carry a lot of data if the source is advanced enough. Right now, our instruments often record just the basic information, the time, strength, and frequency of the burst. If there's a deeper message hidden inside the signal, we might not be collecting enough detail to even know it's there. Improving this means building better receivers and recorders that can grab more data more quickly without losing quality. Certain radio telescopes are already working toward this. They scan a wide range of frequencies, but the amount of data these systems collect is huge. For every second of scanning, terabytes of information are saved. Storing and processing that information takes a lot of resources. It also means that some signals could be hidden in the mountain of data, waiting to be found years later by a better algorithm or a faster computer. There's also the problem of signal loss. Space is filled with particles, gas clouds, magnetic fields, and other things that can distort or block parts of a message. If a signal travels for thousands of light years, it could get stretched, broken, or scrambled along the way. Even if it started out clear, by the time it reaches Earth, it might look like static. Decoding a message like that would be like trying to reconstruct a painting after most of the colors have been washed away. It's not impossible, but it's hard. Some researchers are trying to prepare for this by running simulations. They take a message, something simple like a picture, a song, or a piece of text, and then send it through computer models that mimic the damage space would do. Then they see if their systems can still recognize and rebuild the original. This helps them understand what to look for in a real signal and how to improve their tools for fixing damaged data. But again, this is all based on Earth-based assumptions. A truly alien signal could be in a highly exotic format. Language isn't the only challenge. Even if we could read the symbols, we'd still need to understand the meaning behind them. For example, a message about science or technology might talk about concepts we don't understand. It might include ideas that are obvious to them, but completely foreign to us. In the past, we've sent messages into space with pictures of atoms, DNA, humans, and our solar system, hoping that another species would be able to understand what we're showing. But even these symbols rely on shared knowledge. If another civilization used a different system of logic or saw the universe in a different way, they might not understand our pictures either. They might interpret them as art or even as noise. In the same way, we might receive a beautifully structured signal and have no idea what it's trying to tell us. That's why some researchers talk about the need for a cosmic Rosetta Stone, some kind of shared reference point that both sides could recognize and build from. Without that, communication might be impossible. It's possible that the first real alien message will be something we can't understand for years, or even decades. We might detect it, save it, and only later realize what it was. Or it might be something so strange that we don't recognize it. The limits of our technology are real, but they are always shifting, always improving. What perhaps might be most important is to always keep an open mind. What do you think our odds are of finding an alien signal this century? Comment below, and if you enjoyed the video, consider leaving a like and subscribing to the channel. Thanks for watching.